So for this talk, we won't talk about mostly about the InSight mission, but more about something that we wanted to present you. So we want to talk about life on Mars, and for this we will talk about three main subjects: water on Mars, looking evidence on Mars, and to finish we will talk about sending men on the Mars. So, but first I want you to welcome Raucourt, who will talk to you about a quick update on the InSight mission. Thank you.
So I will present you pretty fast the InSight mission. So maybe most of you don't know very well this mission, so it's pretty basic. So it has been a big human adventure for us over the last 8 years. So we started in 2010 with the proposal, and the launch will be this year. So, but before these 8 years, it was already a very long way before starting. So you had the first seismometer that was sent to Mars with the Viking mission in the late 70s. Then later there has been another launch in '96 with IPGP contribution already. And since those two launch, there was no other launch with a seismometer on Mars. There has been a lot of proposals, there has been a lot of Phase A, Phase B projects, but all has stopped. Viking never recorded any quake because of the poor installation of the seismometer, and Mars 96 went into the ocean. So InSight, what it is about. So the goal of this mission, the science goal, is to investigate the interior structure of Mars and to study what are the processes and that lead to the planet as it is today with its internal structure. So we will use for this seismology, of course, precision tracking to measure the small oscillation of Mars around its orbit, and heat flow measurement. The important thing from the science point of view, it's not a mission only about Mars, it's about how terrestrial planets forms and evolves. And this is really what is the science target for this. So it's a discovery mission, so it's a small mission for NASA. And the goal is something comparable to the experiment that was done with the geophysical package of Apollo. So this is a bit more details about the science goal. So it's really to understand what is the structure inside Mars. And so you have here all the science goal as it has been formalized in the proposal. And here you have the numbers of what we expect for the accuracy, what is the knowledge we have today, and what InSight will bring on the science. And so most of this is addressed by the seismology experiment. And so you have a question about the crust, how thick it is, about the mantle, is it an homogeneous mantle or is there any separation? What is the size of the core? What is the state of the core? And so on. Just a quick overview of the mission. So we will launch with an Atlas V from California. It will be the first time that a planetary mission is launched from Vandenberg launch base. Then we have 6 months of cruise. It's a very classical trajectory for Mars. The EDL system is a refly of the Phoenix mission that has landed on successfully in the late 90s. And so we will land in Elysia Planetium, not very far from the equator here. During the entry and descent, there will be 2 CubeSats made by some US students to monitor the descent, but for all the engineering purpose, of course, there is the more classical relay thanks to MRO. We will talk a little more about the deployment, but then once we have landed on Mars, we will have a deployment and commissioning phase for approximately 1 month, 2 months. And then we have 1 Martian year, so 2 years on Earth for the monitoring, the science monitoring, and maybe more. We hope there will be more. So what is the payload of this mission? So you can see the lander here. So the payload, you have the French contribution. It's not only French. We are 5 countries contributing. I will come back. So this is the seismometer. You have the heat flow probe here, which is from Germany. And so this will dig 5 meters and will monitor the temperature profile in the ground over 1 year to infer from all this measurements what is the mean heat flow of the planet. You've got also RISE here for the precision tracking of the little oscillation of Mars around its orbit. And you have, so this is the main payload, but you have also some instruments that were needed, at least for the seismometer, to improve to monitor the environment of the seismometer. So there is a magnetometer, and you have also some atmospheric measurement with the wind, temperature, that is somewhere here. So now I will give you a bit more detail about SAIS. So SAIS it's a complex instrument. You have 2 parts. You have an electronic box which is inside the spacecraft, and you have the sensor assembly here which is deployed on the ground on Mars. And this is protected by a windshield here. And inside here you can see the long period sensor, and you have the short period sensor somewhere around in one of these boxes here. So this whole instrument is under CNES responsibility as a whole. And you have contribution from different countries. So in the US, the GPL was responsible for all the thermal and wind protection. So you have different parts. So you have some MLI around on the sensor assembly itself to protect the instrument. And you have the wind and thermal shield which will be deployed above. And this includes a skirt that will already protect the seismometer from the wind, so we had to conform on every rocks and so on. The other part, which is from the US, is the tether. It's the cable between the lander and the seismometer head. And this is a pretty complex part because there is a lot of wires, a lot of electrical issues, but also some mechanical one related to deployment. And we need a service loop to avoid that any thermoelastic behavior of the tether is impacting on to limit the impact of thermoelastic on the tether on the sensor assembly. The Swiss from ETH made all the electronic of Insight. So they did the acquisition electronics, but also the DC-DC converter and the box that hosts also the feedback, the sensor feedback board. So it's a nice electronic, very low noise, higher resolution. The German from MPS, they made the leveling system. So this will ensure that the sensor assembly is well coupled to the ground, and it will level the sensor platform. Imperial College and Oxford University made the short period sensor. So it's a MEMS. You have here a coin, so it's made in silicium, and it's a very nice sensor and able to measure with very good accuracy the seismic wave from a few tenths of a hertz up to 10 hertz. And here at IPGP, we were responsible for the long period sensor. So this is what we call the sphere, and inside the sphere you have 3 sensors that were built close from here. It has been a long way to produce this sensor, so I will just give you a brief overview about the history of these developments. So in 2012, that was the final selection phase of Insight, and a few months later, we had the first big anomaly where we had one of the STM of the sensor broke, and so then we had to do some redesign tests. So I will not tell you all the detail about all the anomalies we had, but I put only the major ones that implied some major redesign and delays. And so we had issues with the mechanism, we had issues with some material choice, we had some issues again with the mechanism. We had, this was a big one. The first flight model that was produced was not working at all. And so starting from here, we had a major Tiger team with a lot of, which was a very intense work to target, to troubleshoot what was the issues, to solve it, and to produce the sensor on time. And with, in parallel of this, we had some issues with the sphere, the container around the sensors. We had some issues with the vacuum, with the gaiters. And we finally had a successful delivery, at least for a few months, in July 15. And unfortunately, 1 month after, we found a leak, a very small leak into the sphere, but it was big enough so it's to have a major impact on performances of the seismometer. So the launch was cancelled right after, and then we restarted the project with a redesign of this sphere container, some new tests, new sensor built also, and we had the final delivery of the flight sphere last July. So it has been a long way, but we had a very good team with a very good participation and very good interaction between CNES, IPGP, JPL, and Southern, our industrial partners. And thanks to this integrated team, we really managed to tackle all the issues we had. So we had finally a very successful delivery with good performances. So this is a quick overview about the performances, and basically what we show here is that we managed to have the same performances as the reference seismometers on Earth. And you have here all the sensors that has been produced. You have some test of the flight sphere here. So this is in IPGP, and this is with the lander next to it. And the sensors are still working very well and have passed all the tests. Once we have delivered the sphere, last July, we sent it to Toulouse at CNES, where we were responsible for the integration, test, and validation of the full instrument. So just a few pictures. Maybe I will not comment all of them, but here this is the thermal vac test. It was a big deal because to have some functional test, you need to tilt the instruments because of the Earth gravity, which is not the same as the Mars gravity. And so under here you've got a big tool, a very complex tool to allow the functional test while you are doing the thermal test. You have here some performances tests that was done not so long ago, a few weeks ago, in Black Forest Observatory in Germany. So it's a very good seismic place. And you have here the QM model with the electronic box, the sensor assembly. It's in a vault, in a mine, and you have to bring some flight hardware inside, so you've got a kind of tents to protect all the instruments from the humidity, which is not exactly, this is not exactly what we call a clean room for space hardware. And so we had some performances tests done here. You see the vibe test, and here some integration in the clean rooms in Toulouse. So after this successful integration of SAIS, it has been delivered at Lockheed Martin. Then SAIS was integrated with the lander, that's the picture you have here. We passed all the tests with the lander, vibes, thermal and functional and performances, electromagnetic compatibility and so on. And all the tests were successful. So now the lander is mostly done. It has been shipped to the launch site. And now we have the launch preparation, which is undergoing. And so the launch window will open beginning of May, on May 5th. And so 6 months after, we expect a successful landing on Mars. And then we will have the deployment phase and commissioning phase. So we'll spend 2 months to deploy. So the deployment will take quite some time, but most of this time will be spent to do the commissioning and check that the seismometer is working very well on Mars. So this is what we expect. And after this, we'll have 2 years of monitoring of various seismic events and hope to bring back some nice data from the first time from Mars. So this will be the first geophysical station outside of not Earth, but Earth and the Moon. It will be the first time on Mars. So just a quick movie for to finish this, but you can ask some question if you had any while we are looking this. It's 5 minutes which showing the operation from the launch to the deployment of the instrument. So this will be on May 5 from Vandenberg. So this is an Atlas 5. So it's a pretty big rocket with a small spacecraft inside. So after you will see the separation of the first stage of the rocket. Here you have the spacecraft, and you have the final push to go to Mars. And once we are on Mars, on the trajectory to Mars, we have the cruise stage only, which is following. And 6 months later, the arrival on Mars. And so here you have the landing module. So you can see the heat shield heating when we goes into the atmosphere. And after you've got a parachute which will open after. After you have the lander legs opening and the final phase with rockets. Once landed, the first thing is the solar panel opening to have some energy available. And after we will start the deployment. So the deployment will take a few days because each time you are doing an operation, you need to take a picture and you need to analyze this on Earth to validate that we can go to the next phase. We have and first, before we need to select where we will put the seismometer. So there will be a few pictures of the place that will be analyzed, and we will pick up the best place for the seismometer. So this is the sensor assembly. Then we put the windshield on top of it. And once the seismometer is deployed, we will deploy the heat flow probe.
So you can see this will take 2 minutes?
Yes, a few weeks. No, each operation will take, at each time you grab the seismometers, you take a picture to check that you grab it, and then you give the order to move and to put it on the ground, then you check you are well on the ground. And each time it's nearly 1 day to get the picture, analyze, send the command, and so on. So it will. So, any questions? Yeah. There is very little operation during the flight. There is a quick check of the payload health and a few things, but there is very little which is done. For the seismometer itself, we cannot do anything because there is zero gravity, so the sensors are not equilibrated and cannot work. And the electronic, there will be a quick checkup, and no science really will be done during the cruise. No, we know from other missions that some dust is coming from time to time on the solar panel, but the wind sometimes remove it, and so you have some variation, and the size of the solar panel has taken into account all this.
How to make sure that it will land properly and that does the same thing that for hospital?
So we'll know that it has been landing properly because we will have the data and the pictures. There is a camera on the arm to take some pictures, so that's how we will know that everything is okay. And it will not be the same issue of Rosetta. This lander has been the platform. It's a US design from JPL. It has been, and Lockheed Martin. It has been landing successfully once on Mars, and it has also crashed on Mars because of a software issue. So on 2 attempts, one was successful, and one was a kind of silly mistake that is easy to correct. Rosetta was maybe more challenging. It was one of the first landing on an asteroid. It's much more difficult. It's the different challenges. On Mars, most of the issue on Mars is due to the atmosphere, which is thick enough to burn a spacecraft and which is not thick enough to slow you down before you reach the surface. On asteroids, the difficulty is more to manage the very low gravity. No, well, during the cruise or after? No, the flow of meteorite on Mars is pretty low. I think, Philippe, you have computed this some years ago. I don't remember, but the statistic is pretty low. We will see some impact of meteorites on the seismometer data. That will be one of the seismic sources, and it will be a very interesting one. So there will be some science to do on this, both from the seismology point of view, but also to study the meteorite things. But the likelihood to have a meteorite impact on the lander or the seismometer is very, very low.
Other question?
You said that the deployment will take a few days, but for the seismometers, how can you be sure that there will be not difficulties during the time of deployment of the shield?
We are sure there will be some difficulties. Now there is all the sequence of activities has been thinked with. We do something, we check it, we get some data, we analyze it, we take the decision to move to the next step or to tweak how we will do the next one. And there is a lot of opportunity to rework all this. So for instance, at the beginning we take some picture from different positions. So we have a 3D model of the working place. We will decide where we will put the seismometers. Then the arm will put it where we will ask it. Then we take some pictures to check that it is well in place. And after we spend 1 day with some seismic data so we can check if we are well coupled to the ground, if everything is good. Then there will be a decision to release the service loop on the tether. Then we will take some pictures to check it has been properly done. After we will release the arm from the seismometers, we will take the windshield and we will take some picture of all the seismometers before putting the windshield on it, and so on. And if something goes wrong, we can retake the seismometers and put it a bit somewhere else if needed. I don't remember well, but I think it's 60 sol, no? I don't remember, but it's
about 1 month.
1 month.
In fact, okay, so
That is 1 hour per day of activity.
it is 2 hours every 2 days, and no more than 25 centimeters per 2 hours, and they repeat that down to 5 meters. And okay, and you know it is stopping at 5 meters because of life issues, of exobiology issues.
Thank you, really. One more question. Just to.
Just a question: is it efficient enough to trace the interior structure of the Mars based on seismic data from only 1 seismometer?
Yeah, I think it's a good question. Yes, with 1 seismometer, we will get the interior structure. That's really the goal. So to do this, we specified the performances of the seismometer, so we can monitor with only 1 station all the P wave, S wave, R1, R2, R3. I don't know if you know all this. I don't have the right schematics to explain you, but we will see the wave going around the planet. And so based on this, so we will be able to see this on the biggest quake. So we can retrieve from this the velocity of all the waves. And we can have the localization of the quake, even with only 1 station, at least for the biggest one. For the meteoritic impact, there is something else which is interesting with only 1 station. It's that we will use a MRO to take some picture, and we will try to find the new crater on the pictures. And so if you see that you had no crater, 1 week later you have a crater, and in between a seismogram, you can assess what is the location of the seismic source. And so by combining this, we can find a lot of information. We can also, with only 1 station, use the normal modes. And there is a lot of things to see with only 1 station. And there is, on Earth, there is a scientist of the team who picked up a seismic station on Earth. He selected a limited number of quakes, similar to the one we expect to see on Mars. And based only on those quakes, he finds the Earth structure, the prime model of the Earth, and he finds it pretty accurately with only 1 station and a few seismograms.
Thank you, Sébastien. We're going to. Now we're going to pass to our next presentation. We're going to talk about the water on Mars today. And we are a pleasure to present you François Forget, who will be charged to present those information. Thank you.
Good afternoon. Thank you for being here. So I will be asked to start this after the insight highlights to give you the first talk about Mars and water on Mars, because the topic is a little bit related to water. It's a dream for everyone. But I will talk about all water on Mars. But to start with, I will just remind you, what is Mars? Mars is a small planet. It's not just near the Earth like on this picture. It's 1.5 times more distant from the Sun than the Earth, so it's a little colder. And of course, it's a desert planet. The atmosphere is much thinner. You can see it's 6 millibar atmosphere, mostly made of CO2. But of course, these are lots of differences. But otherwise, if you think about it, the day, what we call one sol, a solar day, is 24 hours and 40 minutes, so it's very close to what we have on the Earth. And also the obliquity the inclination, you know, where that really drives the season on a planet like Mars or the Earth, is about the same, so that you have the same seasonal cycle. Of course, the year is a little longer on Mars because it's further away from the sun, but you have all these common points. So it's easy to imagine in terms of environment that Mars is like a small Earth, but desert and colder with a thin atmosphere. But except for that, meteorology, all the processes are a little similar. If you go on the surface, for instance, one of the first missions that successfully landed when I was a professional, Mars Pathfinder, you see it's a desert, of course. But if you look at the temperature, typically during the day, the surface temperature is up to 20 Celsius. And during the night, it's very desert climate. It's minus 80, typically. And the other big difference, except there is no camel and nothing like that, the sky is always orange, not blue. And the reason why it's orange, it's because always in the atmosphere you have some dust particles that is lifted in such dust storms as you can see here. And I use this picture to also show you that even though it's a desert, like on the Earth where the climate is complexified by the presence of water, oceans, snow, clouds, rain, on Mars the climate is a little complexified by the presence of dust, of course, but also this ice that you see here mostly is actually CO2 ice, frozen atmosphere, but you also have water. And here the little haze on the left, on the right, are water ice clouds. So that's the topic, water on Mars. So don't laugh, because since I've been doing this job, every year or twice a year, so it's been like more than 20 years, okay? A friend of mine say, I have a very funny picture I have to show you, and they send me this picture. And if you go on the internet, you will see 15 versions of this picture. So don't send me this picture. It's funny, but once. So water on Mars. And indeed, in fact, there is a reason, because you always hear about water on Mars. If you pay a little bit of attention to the news, the science news, frankly, in the past 30 years, every 6 months, there is an event, news event related to water on Mars. Sometimes a new reservoir of ice that is discovered, a new proof that there were liquid water in the past. I will detail that. And it's true, every 6 months there is a major discovery related to water on Mars. So indeed there is water on Mars. To start with, I will even say that there is a water cycle, an atmospheric water cycle. Everything starts, you can see here on this picture, taken during northern summer. You can see at the top, this is the pole, and at the pole you have a ice cap, which is a few kilometers thick, which is about 1,000 kilometers across, the size of France. And this is actually a big pile of ice. If you zoom, you see that you have lots of ice interacting with the atmosphere. And every summer, of course, it's heated by the sun. It's in contact with the atmosphere. This ice in the thin atmosphere, it doesn't melt, of course. It will evaporate, and it will feed the atmosphere with lots of water vapor. It's transported by the atmosphere, and it can form clouds and so on. This is a quantitative view of that. These are records of measurements of water vapor in the atmosphere. These two plots are, one is the zoom of the other one, is an average plot of the water vapor as a function of latitude and time, of season. And I'm sure you understand. Will that work? Maybe I can try. Oops. Here it is. That this is northern summer. This is when the ice is exposed to the atmosphere. You have lots of water vapor which sublime, transported by the atmosphere, and you have a cycle every year, the same water cycle. So even though it's not much water vapor, you can see here the unit we use is precipitable micron. In other words, if you condense all the water that is, for instance, here on the surface, it will be a 15 micron layer. That's not much, but that's because it's relatively cold in the atmosphere. It's enough to form clouds around mountains. This is, of course, Olympus Mons, which is 20,000 meters high, and you have lots of, for the specialists, adiabatic cooling and cloud formation. You have hazes in the morning, just for the exact same reason as on the Earth, cold air flowing down in the valleys, and condensation of water. You have frost, just like on the Earth, actually Viking London 2, which took this picture, was at 48 degrees north, which is the latitude of IPGP in Paris. And every morning in fall you see frost, and throughout winter you have frost all day long, a little bit like in France. And we can model that, so we have meteorological model just like on the Earth, and we can simulate all the process I just described to you, the sublimation, the transport by the atmosphere, the condensation of clouds, of frost, everything. And that works fine. So we have all these, imagine, meteorological models. You see the clouds forming. These are low pressure, anticyclone, high pressure. You have lots of process going on. And when we do that, we kind of understand what's going on. These are the observations, again, the amount of water vapor in the atmosphere, and this is the simulations. Very easy to get that, because you have this release of water vapor, transport, so we kind of understand the water cycle, atmospheric water cycle. Now, what about the surface? If we look at the ice that goes on the surface, that's the plot. This is from a model, but it's also absolutely confirmed by the observations that we get with spectrometer. This is a plot about the distribution of water ice frost, like the one I just showed you here, as a function of latitude and season. And you can see that you have some frost, not much. Huh? If these are, I think, microns. So you get to a few microns of ice on the surface, but that's not much, like here. And but if you look carefully, you can see that except at the pole, you never have accumulation of water ice. There is no accumulation of ice outside the polar regions of Mars today. As a result, so it's really, really a desert. And that's why very often you see a picture, what you see is a big desert. If you don't see the poles, you don't see ice. Yet, if you look carefully, if you're a geologist, maybe some of you are geophysicists in the room, you can, if you look carefully at the surface, you realize that below the sand, below the rocks, in many locations, not everywhere, you see traces of glaciers. You can see moraines in the southern hemisphere. In many areas in the northern hemisphere, you can see rock glaciers, very similar to the one that we have on the Earth. So these are glaciers covered by rocks, so the ice is isolated from the atmosphere. Otherwise, it will not be stable, as I told you. You even see big rock glaciers in the tropics. In fact, in this area where you have the big volcanoes, I mentioned Olympus Mons, you have 3 other volcanoes which are above 20,000 meters. And on the western side, we have discovered a lot of moraines and faces and lots of clues that suggest that this yellow area on this geological map have been really controlled by glacial activity. But nowadays, you don't see any more ice. And even more, it has been discovered that about 1/3 of the planet, below what is apparently sand, dry sand on the surface, just a few centimeters below, you have lots of ices, lots of water ice. So how have we discovered that? Well, it's thanks to nuclear physics. This is done by using a neutron spectrometer. It was on the spacecraft Mars Odyssey, a NASA spacecraft. They had a neutron spectrometer. The principle is the following. On a planet like Mars, like on the Earth, but on the Earth the atmosphere is too thick to really use this method, you have cosmic rays that hit the surface, they go deep, and when they hit a nucleus, they eject neutrons, and you have constantly a planet like Mars, like the Moon, that radiate neutrons. And you can monitor the neutrons from space and see what you get. If there is no ice, you get a lot of neutrons. But if you have some ice, that means you have lots of protons, nuclei of hydrogen molecules. That's what you have in water ice. Then it turns out that you can demonstrate that the neutrons, they tend to hit the fast neutrons to hit the protons in the hydrogen molecule. In the hydrogen molecule. They bounce around and they're slowed, and you have less neutrons and they are slower. That can be monitored. And doing that, it was a very big surprise to discover that everywhere here where it's blue, you have a lot of water. In other words, it was discovered that in all these areas, you have a few centimeters of sand, and below that, it seems that you have lots of almost pure water ice. That was a surprise. So at the time, we are in 2001, it was decided through a selection process that it will be a good idea to send a spacecraft somewhere there to check if really you have ice. Can you really trust the neutrons, and what is the origin of this ice? So on May 25, 2008, the Phoenix lander, which is the same kind of spacecraft than InSight that you have just heard of, this one successfully landed in this high latitude region. So it was what will be the first polar view of Mars. And in fact, this polar view turned out to be typical of the polar region with that's a joke from the PI, but indeed, you see that this terrain is really characterized by polygonal structures, and this polygonal structure on the Earth and on Mars are really characteristic of an ice-rich ground. For instance, if you see a rock glacier in Antarctica, you see this polygonal, which is due to the heat contraction and all the thermal effect of ice that creates this polygonal terrain. Not only that, very quickly, the spacecraft used its camera to check if everything was okay, and below the legs, you can see the legs of the spacecraft. These are the thrusters for the landing, and the thrusters have moved away the sand, and below the sand, just as expected, almost pure water ice. They also had a shovel, and they were able to dig a little bit and find the pure water ice. So, indeed, you have a third of the planet Mars covered with water ice below a few centimeters of sand. So where is the ice coming from? The Phoenix team, of course, did a lot of investigation, and if you look at their papers and their conclusion, they consider that the ice, the almost pure ice that you have there, must come from the atmosphere, and it's because you have always some water vapor there. It can diffuse through the regolith. It tends to condense because on average the temperature is lower there than there, a little bit like, cave on the Earth. And you have an ice table that forms. Okay, that's every model will agree on that. But not only that, they assume that not only from ice, cement, and salts, but it will segregate away the sand particles, the salt particles, so that you will have almost pure ice. So they have been working on the process, and that's their theory. They assume that you will have similar process that what you find on the Earth, ice lenses, and sometimes, so of course here you have some erosion, in permafrost regions where you have a very cold terrain with in equilibrium with the atmosphere, frozen ground, and sometimes processes that move away the rocks and you have pure ice. The problem is that to get that on the Earth, it really requires melting, freezing, melting, freezing. So that suggested that you had some melting, freezing processes. It's debated. An alternative to that, something I've been working a lot on, is the idea that very simply what you get here are the remnants of past snowfall and ice mantling because of meteorology, and then sublimation when the climate was drier and hotter, and snowfall again, and that will make a pure water ice layer. And in fact, recently, a few weeks ago, there have been a paper showing and discovering for the first time water ice not at the pole, on a crop, on a few outcrops. I really copy-paste this very quickly. This is the paper that was published. I don't know if you have the date, but it's really a few weeks ago. And there, in some at mid-latitude regions, they found cliffs where you have water ice exposed. As I told you, this ice is not stable. It tends to sublimate, and the ice to accumulate at the pole, but it's very slowly sublimates. So you can see slowly the cliff moving away, but you have exposed water ice. But the point is that the conclusion of this paper is that, wow, you have cliffs that are 100 meters of pure water ice. For them, it's the proof that this mystery of water ice is not coming from the diffusion and the segregation of ice-cemented soil, but it's more the remnant of a big snowfall and mantling and glaciation of this area. How is that possible, by the way? Why do we have suddenly snowfall where it's super dry now? Mars should have looked like that in relatively recent past, a few thousand, hundred of thousand years ago or million years ago. Well, of course we have an idea. On Mars, we know that in the past millions of years, the obliquity have varied a lot, between typically 15 to 35 degrees in the recent past and between 25 to 45 more than 5 million years ago. This is a big variation of the axis of rotation. That completely changed the season. On the Earth, the oscillation of the obliquity is much lower. It's between plus or minus 1.4 degrees. And yet, these variations is supposed to be what has been controlling the, as you all know, Milankovitch cycle and the ice ages on the Earth. So, of course, one can expect ice ages on Mars with such a lot of variation. And indeed, if we do model that, we can take the same model that I just described to you, but we change the obliquity, for instance. We do find that indeed at high obliquity you have much more water vapor, which is released if you assume that you have a water ice there. It's a much wetter. I won't have time to describe that, but we have published a lot of paper. But we do find that, yeah, at some point the ice is no more stable there. It tends to make the glaciers that I've just described to you. We have a good match. We understand well the data. And in many simulations, we are able to make big deposits at high and mid latitude that somewhat look like, I won't describe that, these are maps of output of some numerical simulation of the accumulation of ice, the ice glaciation of this area, and we tend to understand how Mars could have been glaciated in the past, how Mars could have looked like that with water ice there in a few million, hundred of thousand years ago. The debate is still going on. I told you, many scientists believe that this process is not the origin of the ice observed by Phoenix. We will know more soon. We have right now an orbiter around Mars, a European orbiter, Mars Trace Gas Orbiter, and is equipped with a new kind of neutron spectrometer, like on Mars Odyssey. I described that to you before. But this time it is supposed, it's a Russian instrument. They're good in nuclear physics. It's supposed to give you a map of this subsurface ice, but with a resolution 10 times higher than what we have now. And maybe this will give us a clue. This is a completely artificial image. Give us a clue about what really controls the deposition of the ice and maybe help us to solve this debate, this going on debate in the Martian community. But of course, if the topic is life, everyone is interested in liquid water. Can we have liquid water on Mars? Well, if you look at this diagram, this is the water vapor. I'm sure you're all familiar with this kind of diagram. This is vapor pressure of water as a function of temperature. You realize that on Mars, at least in some valley, not in the mountains where the pressure is low, but in some valley, you can have pressure up to 10 millibar. Every afternoon, the temperature goes above 0 degrees Celsius, so in theory, you could have liquid water. If you're there, that means that in a valley in the afternoon, if you put a glass of water on Mars, the water will not boil instantly. If you put it there, it will boil instantly. If you put it there, it boils, but not there. On the other hand, it will evaporate. It will evaporate very quickly. It will also freeze by evaporating because of the latent heat consumption. And the reason is that to not evaporate, to be stable like a glass of water could be stable here, the atmosphere should be, if you read carefully this plot, the vapor pressure should be equal to the absolute pressure. In other words, for a water, unlike on the Earth, for a glass of water, liquid water to be stable somewhere on Mars, the atmosphere should be composed of almost 100% of water vapor. Of course, it's impossible. It's mostly CO2. So a glass of water vapor would evaporate relatively quickly. That's why we have never seen any liquid water anywhere on Mars. Yet, there have been some interesting findings. An example was, this is back 18 years ago, a big discovery by a camera on Mars or observer, Mars Global Surveyor, which was the finding of these gullies, which really look like debris flows that would have been formed by liquid water. So that's why the title of this paper was evidence for groundwater seepage and runoff and so on. If you look at the image, it's really striking. It really looks like beautiful creeks. You can see here with some sinuosities. That's if you're a specialist, really suggest that you have something with a viscosity that suggests the presence of a liquid. They really look like many of the debris flows that you find in many regions on the Earth, including in Arctics, where you have debris flows like that, and they're really made by melting of snow in spring that lubricate all the debris, and up you form debris flows like that. You even find very intriguing debris flows like that on dunes with lots of sinuosities. They're really intriguing, nothing like that on the Earth, but all the studies suggested that you need a flow with very low viscosity mixture material, and suggesting that you need liquid. So how are gullies formed? The first suggestion by several papers was that, you must have an aquifer just near the surface, and from time to time the pressure is so high that you have water going on, you have this kind of image, this is Mars, it's incredible, liquid water. This is what making, but no, quickly, not that quickly. It took 10 years for people to say, no, it's not possible. But many scientists worked on it. You have lots of papers working on this suggestion. One of the reasons it doesn't work very well is that you see debris flow in many locations, not related to any kind of aquifer. It doesn't make sense. But on the other hand, you see them especially in southern hemisphere, in a very specific range of locations, and very often, at least at low latitude, on pole-facing slopes. So you can see it's more or less controlled by a climate process, insolation process, rather than a groundwater, volcanism, or whatever. In a few years later, with my colleague François Cottard, Nicolas Mangold, and Jean-Pierre Pelvast, we published a paper in Science, and we were convinced we had solved the problem. Really, we had found that it could work very well. Oh, sorry, this is in French. At high obliquity, you remember at high obliquity you have this ice-rich planet. This is when you have the glaciation. And then you can really demonstrate that on pole-facing slopes, exactly like observed, it's at the same time very cold during winter, very hot during summer. You have lots of ice around, it melts, everything is good to form debris flows. So we really published this paper that was the reference, very humbly, to explain the debris flow, so the gullies. And I was convinced of that, but even in this paper we wrote that if we find gullies forming on present-day Mars, that will show that this suggestion, which really requires obliquity, is not working. And guess what? We found new gullies forming. This is two pictures separated by a few months, a few years, and you can see that this is one gully, and a couple of years later, I forgot, that's 2 Martian years later, you have a kind of new gully here. And since then, this is the first case we find. We find many cases of beautiful new gullies. And when the people using the camera explored that in more detail, they found that the new gullies tends to form when you have CO2 ice frost. Nothing to do with weather frost. When the temperature is minus 135 Celsius. So there's no liquid water at this temperature. How is that possible that this seasonal dry ice, about 30 centimeters thick, can form these big gullies? So we've been working on that. I can advertise some work we did with Cédric Pilorget, where we did model all the physics going on when you have the CO2 ice on the sand above ice, cement, and soil, remember? And when we modeled all that, we found that at the end of summer, when the solar flux, at the end of winter, when you heat the CO2 ice, remember, you tend to overpressurize the ground below to put CO2 ice in the pores, and at some point the pressure is such that everything breaks. You have a huge amount of gases that must go through the material, and we believe that you fluidize the soil and you create these gullies. They look like they've been formed by liquid water, but in reality they are formed by fluidized gas. That's my. I'm convinced of this theory. And a good analog will not be then the gullies formed when you have melting snow. A good analog will be more like paroxystic flow. I know that some people at IPGP has been working on this kind of things. So these are paroxystic flows. In other words, when you have a slope on the volcanoes that is disturbed by a little bit of hot gas, not much. These are really low gas-rich paroxystic flow, not much gas. That's enough. And the hot gas is enough to really create debris flow that can flow on kilometers, hundreds of meters, even on flat terrains, and forming these gullies with levées, and they look a little bit like what we have on Mars. So, no water. I believe that gullies are not related to liquid water at all. Another thing that has been suggested to really look like something related to liquid water, what was we called in our jargon, recurring slope linear. Or RSL. If you go to a Mars meeting, everyone talk about RSL, as if everyone knew it. RSL are these. You can see a series of pictures separated by several weeks, okay? And it seems that you see something dark flowing down. And it's not easy to know what it is. The first suggestion was could be due to water, but of course, it's impossible to have water there, especially we see this RSL flowing. Another example here. On the slopes in summer when it's the hottest, where the temperature is well above 0 degrees Celsius. So if you don't know about the physics, you say, well, cool, that means you can have liquid water. But on Mars, that means you're super, super dry. It's almost impossible to have liquid water. Yet the theory was that you have salts there, and these salts get liquefied by the water vapor, and in some way can flow and form these humid things. Indeed, in Antarctica, for instance, you can find stuff that looks like that evolved just like that. And this became very famous a little more than 2 years ago because of this paper. This is a student, and Alfred Mathigoen is the PI of the camera that all discovered that. And they wrote a paper, Spectral Evidence for Hydrolytic Salts in Recurring Slope Linear on Mars. There I found, doing spectroscopy, that not only you have this dark stuff, but this dark stuff looks like salt. They didn't see water. They see, these are salts, these are perchlorate. They could be liquefied by a deliquescence of salts due to the presence of water and make liquid, super salty liquid water. But what happened is that when this was published, NASA decided to do a press conference. So they announced, we're going to do a press conference about liquid water on Mars. And then all the news people become crazy. They say, wow, they've discovered frogs. And on many, many websites and journals, they say, Mars new major science finding to be announced Monday. There were huge, before even the results were described, there were a very big buzz. So maybe some of you remember that. And then the press conference came. So my friends, my colleagues, Alexandre Adoua, Alfred Mathigoen, they were actually in France. They did the press conference remotely, and the room was full, and people were asking, do you find frogs? Do you have fishes? And no, they just find salts. So the newspaper, they had no choice to announce very exciting findings. Definitive liquid water on Mars. Confirms the best ever evidence for water on Mars. Frankly, me, and even more than me, my colleagues who are specialists for spectroscopy and the physics on Mars, they were super skeptics. I mean, this is really poor. And since then, in fact, no, the leading theories, these are recent papers, about the formation of this recurring slope linear, they don't need liquid water at all by rarefied gas-triggered flow. This is a very good paper by Frédéric Schmidt in Orsay at GEOPS. This is, you can see, granular flows indicate a limited role of liquid water. If you read the paper, that means no liquid water is needed at all. So, no liquid water with this information, in my opinion. So can you have liquid water on Mars? Maybe deep in the subsurface, at very low, at several kilometers deep, you have internal heat, and it's pretty warm. It should be pressurized. You should have lots of ice above, and we expect that it's possible to have aquifers. On Mars Express, the European Space Agency orbiter that has been orbiting Mars for 15 years, there were a radar named Marsis designed to find these aquifers. Nothing was found, but we also discovered that the Marsis was not able actually to find them. So there is no proof that there is no aquifer. InSight, I've been told during lunch, will be able, through seismology and through measurement of the magnetic field, maybe to detect conductivity and also the special thermomechanical properties of when you have a hydrated liquid water in pores. Maybe we'll be able to detect the presence of liquid water. And so maybe we'll know more. Meanwhile, another way to investigate that is that this is also exciting, because if you go to liquid aquifer in the subsurface on the Earth, this is full of bacteria. So we all dream of Martian bacteria somewhere there. And in fact, it's impossible to drill there and check if they have bacteria. But the spacecraft just mentioned, which will start its scientific mission in the next days, in fact, the Trace Gas Orbiter is equipped by 6 spectrometers, which are designed notably to smell, to spectroscopically characterize the presence of trace gas, and maybe see if there is some biological activity that may be detected through the trace gas that could be released by this biological activity. It's very, very speculative, but maybe we'll see something going on. Okay, I will now finish. How long? Yeah, I'm too late. I'm too long. But by mentioning the fact that, of course, as I told you, that there is almost no hope of liquid water in recent Mars. But what about billion years ago? I'm sure you all know that billion years ago, Mars was a very different world. We know that because if you look at the topography, you can see that about half of the planet is heavily craterized, and that means that it's a very old surface, dating back from the late Helium bombardment, typically 3 or 4 billion years ago. And when you look at this whole area, you find lots of clues about liquid water flowing. Well, first, very often people look at this clue here. If you look at this area here, and do a little zoom, you find very interestingly lots of clues about water or something flowing down there. This is big, okay? These are very large-scale things, and you can see that there have been a lot of water, what we consider to be actually catastrophic flows of liquid water flowing there. If I show you a picture of this area, this is how it looks. You can see a lot of the surface has been carved by a very intense flood. And in fact, the theory to explain that, by analogy to what has been observed sometime on the Earth, this is more due to some kind of volcanism interacting with water ice and creating a catastrophic flow and carving the surface in such a way. But that doesn't mean at all that the water was stable. In fact, this could be formed today, even though this activity, probably most of this activity has been dated back to about more than 3 billion years ago. And you can, if you zoom, you see all the flow I've carved. So these are called outflow channel. They're very often shown to show that old Mars, ancient Mars, was suitable for liquid water, but not really. What is more interesting, if you look at this old area where you have lots of craters, is that between the craters, very often you see lots of clues about liquid water. In many areas, you see valley networks, dry riverbeds that are really seems to be characteristic of a planet which was really different than today, with precipitation, runoff, flowing of water, a lot of water to carve all of this river valley. Sometimes in the craters you see layered deposits that really look, if you show that to a geologist, maybe some of you, they will say, oh, these are lacustrine deposits, of course. So they look like ancient link banks. You have beautiful hills that are made by these apparently lacustrine deposits. Of course, initially, when we discovered that with a high-resolution camera, we had to be a little careful, because this could be made by Aeolian deposits. It could be, stratified dunes carved by erosions. They could look the same. We have billions of years to make them. But, of course, in some location, really the smoking gun was there. This is the edge of a crater named Hesbelvarde. You have a water river from the left, and you can see a delta. You can see the size. It's not very big, but this is a delta. And when you look, you have lots of deposits, alluvional deposits. And if you look carefully, for instance, here, this is really characteristic of old meanders on the earth that has been cut. So you need lots of time to form that and accumulate lots of sediments. A river, a delta, a lake were there sometime in the past. You also have lots of mineralogical clues about the fact that there were lots of liquid water on the surface of Mars at the time. Maybe in the subsurface, sometimes it's ambiguous, but for instance, these are maps of the clays. Clays are very common on the Earth, as you know, but you need liquid water most of the time to alterate, for instance, basalt to make clays, and this suggests that there were, in some location, a lot of liquid water, at least on the surface or sometime in the subsurface to form that. So, that's a mixture of French and English. 4 billion years ago, or a little more, maybe Mars was like that. We don't know. It's not easy to understand what was going on. There is a big mystery. That's my job, to understand how could the environment and the climate be suitable for liquid water. It's a big mystery. Very difficult to simulate a climate warm enough to have liquid water. We need to combine a lot of processes, greenhouse effect of not only CO2, which is what we assume to have been the Martian atmosphere at the time. We need to add some other greenhouse gas, otherwise the greenhouse effect is not sufficient to have temperature high enough for liquid water. Sometimes we add the greenhouse effect of clouds. Sometimes we think that the impacts of asteroids, all these craters were formed by impacts, and when they impacted, they escaped some ice, increased the temperature. This is a big investigation going on, but right now it's still an enigma. How could have been the climate system of Mars at the time able to have conditions suitable for liquid water? It's very difficult because Mars is further away from the sun, and the sun was relatively fainter then than now, and it's very difficult. Yet, we have to investigate, and one way to investigate will be to send cosmonauts, astronauts. You can see they have a microscope in their electronic microscope. They look for bacteria. It's very exciting. But we can't do that yet. Francis, who's just arrived, will talk to us about human on Mars later today. And meanwhile, we cannot send geologists, but we can send robots. They're not French. They are Americans. And first you had the 2 Mars exploration rovers, Spirit and Opportunity, and of course the big one, Curiosity, that will be described later by Caroline Freissinet, who will be after me. In agreement with Caroline, I've added a few pictures to show you what happened, what Curiosity has done. So Curiosity landed in a very interesting place. It's a big crater, and in the center of this crater you have a 5-kilometer high pile of sediments, big mountains, full of sediments, either alien or lacustrine. And Curiosity landed on the side, has explored a little bit, and now is trying to move up to explore different layers of the sediments. Go back in time. This is Curiosity on the surface. Another rover was sent to take this picture. No, it's a selfie. And of course, this is the big mountain I just described to you. You can see all these sediments. A very interesting place. Most geologists on the Earth would agree that these are sediments at the bottom of an ocean, typically. Maybe frozen dunes, but stratified dunes. So Curiosity, as most of you know, is equipped with a lot of equipment. You have, in particular, a French contribution in this. I don't know if you can see an instrument that does laser-induced breakdown spectroscopy, and you also have a system to take some sample in the rocks. Is it down? No, it's going to do it. So you have this big arm, robotic arm, which is very complex, very expensive, and we can drill a little bit, take some samples. And then put it back and to be analyzed. And Caroline will tell you all about this. Meanwhile, what about liquid water? Well, one of the first things that early discovery of Curiosity at the bottom of this crater was to go across a creek, how do you call that, an ancient creek, where you have pebbles that apparently, if you compare with the Earth, it's a little bit like that. You have pebbles that were rounded by flowing in the liquid water, and it was a very striking, nice discovery that to find, indeed, there seems to have been more than 3 billion years ago, a torrent of liquid water there, and you have pebbles, like on the Earth. Then Curiosity went to a very old area that is called Yellowknife Bay, and then they did a lot of geological, mineralogical investigation, and in this nice area they found lots of stratified sediments, some veins, and the conclusion was this was used to be a lake of liquid water, not too acidic, so interesting place. Now Curiosity is climbing the hill, the mountain, and is now going through more sediments. They are beautiful, but if I understand well, most people consider all these sediments are actually aeolian deposits, not lacustrine or something deposited in liquid water. It is assumed that Curiosity has to go a little higher to find clays, sulfate stuff that must have been deposited by liquid water. I want to say a word about that. In 2020, there will be another kind of Curiosity rover named Mars 2020 so far, sent by NASA with a French contribution again, and of course a big rover by the European Space Agency with a strong French contribution, and that will also be sent in 2020 if all goes well. And also this rover will investigate a very ancient region on Mars full of clays, full of hydrated minerals, and that will be interesting. That's it. Thank you very much.
Thank you, François. Best for just some questions? Anyone? To ask François about...
I was just wondering, if there are not marine deposits, where is the layering coming from? In these alien deposits we see at the end?
Well, this is, if I tell you, imagine a stratified dunes. Maybe you have some experts that called, but these are a series of alien deposits and the stratification may come actually to climate cycles. For instance, it can take a lot of time to make that. For instance, due to the Milankovitch cycle, the oblique cycle I described to you, that could be the signature of these cycles. That's absolutely a possibility that is very popular in the literature. So you have cycles of wind and deposition and stratified dunes.
Thank you. Other questions? Okay, so... Okay.
What are the different mechanisms without water for this RSL you described?
Oh, that's a good question. Well, the idea is that, as I told you, the RSL tends to be observed on very warm slopes, sun-facing slopes in summer near the equator, where you get really warm temperature. And the suggestion is that when you eat, you still have a strong diurnal cycle, in particular in the shade of rocks that are seen on these slopes. And if you model that, and that's, for instance, what has been done by Frederick Schmidt, you find that this goes along with lots of motion of gases, because you have heat, you have hot gases going on, you have a kind of pump, which is done when you model that. And you find that in conditions on Mars where everything is relatively quiet, this RSL has been found to form mostly on slopes which are not far the repose angle of repose. And you can find that these motions due to hot atmosphere, this cycling, this pumping, can destabilize the grain. And when they are destabilized, you can show, there have been some lab experiments, that then you have a kind of sorting and you tend to have the bigger sand, soil particles to stay above and the smallest to go below. That's induce a change in albedo. That's why you find this slightly darker. You have to understand the contrast is a little enhanced in this imaging. So you have a slightly darker avalanche. That's actually seen very often if you look at it. So you have this darker form that creates. The model seems to work well, explain well the orientation and the timing. And then they slowly fade away because you have dust coming from the atmosphere that accumulate there until you have another destabilization, and then the big particles goes above again. So that's the mechanism. Did you get it?
One argument of Frederick Schmidt is that to demonstrate that it's not due to liquid water, that is observed that RSL are only observed when the slope is beyond 27 degrees. Below you have no RSL. So with water, it's possible to flow at low steps. And though, so this is a key argument to say that it's triggered by only purely dry system with gas, as say François.
In fact, the point that you just said is actually the main point of the the first paper I've shown on the left by Colin Dundas. And this is where he shows that it's really at low. In fact, Frederick Schmidt tried to show that this mechanism will work on slopes which are a few degrees below the angle of repose as observed. But Colin Dundas did more investigation and find that really this recurring slope linear are observed on really on slopes which are really close to the angle of repose, to the a slope that is willing to be destabilized. And so, if it was really related to liquid water, it should have been a different story. So you can read these papers, and it's really quite, I think, convincing.
I know about the experiment on this kind of condition. What about the laboratory experiment to try to reproduce this kind of pattern?
In fact, I don't show it, but there is in the Frederick Schmidt paper, they refer to another paper that is actually showing this kind of experiment. Again, it's the thermal cycling. The venting due to this thermal cycling that destabilizes the grains. On the Earth, it doesn't work well, but at low pressure, it's quite efficient. Okay.
Do you have an explanation for the big difference between the topography of the northern hemisphere and the southern? Since the northern is really smooth and the southern has a lot of impact.
Well, this is really, it's as you say, it's a question of age. So what happened is that southern hemisphere is very ancient, so it's carved and marked by lots of impacts, as you can see, because this surface has not been resurfaced since the late heavy bombardment, typically 3.8 billion years ago. This is when you have lots of impacts, and this area is like the moon, if you want. Whereas the volcanic region, as you can see, where you have less crater, and the northern hemisphere is much more recent. You have a combination of two things. You have first, it seems in many locations you had some resurfacing by lava flows. But in addition to that, this is quite ice-rich, and there are lots of speculation about the actual, this blue zone is also largely, as I discussed, covered by water ice. Even you can speculate, I'm not too sure myself, but it's a very popular speculation, that this used to be filled by somewhat water. I told you there were this catastrophic flow, remember? And it seems the amount of water that flowed there was significant. That also covered the area by water. No, it's ice, it's frozen, it's covered by some lava and rocks. So it's a recent surface, it's not very, so you don't have much crater, so it looks flat. If you look at the moon, to be honest, just the moon, without talking about water, you have some areas which are super rich, crater rich, and the sea, how do you call that on the moon? Yes, seas are quite smooth because they are more recent and less carved by impacts from the past.
We're running a bit late on it now, so it's just going to be the last question.
What makes the obliquity of Mars to vary so much?
That's a complex question. It's if you do the calculation. So we have the The real specialist of this is French. His name is Jacques Lascar, and he has studied that a lot and demonstrated that for most planets, actually, the size of Mars, because of the various forcing due to Jupiter and other natural forcing, they tend to vary. The obliquity will tend to vary a lot like that. However, the Earth will be like that if there were no moon. It turns out that the moon, the presence of the moon around the Earth, exerts an additional torque, which stabilizes and prevents one of the processes that make Mars to do that, and prevent the Earth to do that. If you take, according to Jacques Lascar calculation, if you remove the moon, the Earth will do that. No, that's a simple answer. If you want to see the details, you can read the papers. And what's interesting, it's a real solid mechanic problem with forcing and resonance, and you can see that depending on the rotation rate, the resonance with Jupiter and so on, you can be in a regime where you have this obliquity varying a lot, or you can be out, and it will not take much for Mars to be quite stabilized. And the same for the Earth, I will say. So the detailed answer is quite complex, but it's interesting.
Okay, thank you, François. Well, now I have the pleasure to introduce you Caroline Freissinet, who's going to give us some evidence of life on Mars.
Ouais, ça marche. So good afternoon, everybody, and thank you for the organizer for inviting me to this conference. And I'm going to talk about how we look for evidence of life on Mars, quite general. So my first slide is about something that I'm not going to talk about. But it's so important that I really want to mention it, is that looking for extraterrestrial life begins with understanding the origin and evolution of terrestrial life. So a big part of the extraterrestrial life investigation is to investigate life on the Earth. And it's not that we're going to look for extraterrestrial life as the same kind of life than the one we have on the Earth, but we need some background to know what we're going to look for. And so that's a very important part, but I'm not going to talk about that at all. So let's go to extraterrestrial life. Looking for this type of life, it's not only looking for life itself. It's a whole thing. And the first is to look for the context of the location where we're looking for. The context is a geology consistent with the long-term preservation of the remnants. If there was life in the past, but the geological settings renew everything and we cannot find this traces of the past life, there is no point of looking there. So the context is one of the big things to look for when we look for extraterrestrial life. The other thing is the habitability. So what's the condition, where's the condition all gathered together at the same place at the same time for life to emerge and to sustain in time. And the different criteria for habitability, it's long-standing water, so that's all what François just talked about. And energy, we need a source of energy, source of energy for life to appear. Mild conditions of temperature, pH, pressure, salinity, and so on. And the presence of simple and complex organic matter as building blocks of life. It's necessary, so kind of food for life. And all these habitability criteria has to be stable in time in the environment. So that's the other thing to look at for looking for extraterrestrial life, is habitability. And the third thing is to look for evidence of life, traces of either present or past life at this place. And I'm going to describe just a little bit one mean we use for looking for this life part, like is there biosignature somewhere. The first one is to look for organics, because organics, I will discuss that more in detail in the next slide. It's really the grail, because it has to be present to be food for life, but it's also the remnant of a possible life. So it can be one or the other. It can be chemistry unnecessary, but it also can be some degradation products of life. So that's why it's very, very important. And how to differentiate between chemistry and biology when we look for complex organic compounds. One thing is to look at the composition. When you have a chemical distribution of molecules, so here, for example, I think it's what is that? Carboxylic acid, or it's complex molecules, and that's the number of carbons that you see here. So when you have a chemical synthesis of this carboxylic acid, you will have a Gaussian distribution of equal number of carbons. So you will have 10, 11, 12, 13 number of carbon in your molecule. When you look for life, because the life synthesis of carboxylic acid has enzymes that build molecules 2 carbons per 2 carbons, you will have a distribution with only even number of carbons in your molecule. So looking for the difference of distribution between life type synthesis and chemical type synthesis is one of the way to differentiate between the biological or abiotic origin of your molecules. The other thing is chirality. I'm very interested in that part. Chirality is the fact that molecules, it comes from the Greek kyros, that the hands. And it's the fact that molecules will exist under 2 different forms that are symmetric in mirror but non-superposable. And these molecules, when you synthesize from chemistry, you will have 50% of each form, left and right. But in life, only one of the 2 forms will be used. So it's for amino acid, it will be only the left form. So all the amino acid will be under the left form. So if you find only left amino acid, that would mean that these amino acids, they are degradation products of life. If you find a 50-50%, it can be that there is a process that made the 50-50% again from life, or it can be some chemical synthesis from simple molecules to amino acids. So that's more complicated. But if you find like just one of the 2 forms, that's very, very strong indication for life. And then isotopes. In life, you will always use lighter isotopes. That's the easier way to handle chemical reactions in living systems. So we'll look for fractionation in isotopes and looking for fractionation towards lighter molecules, lighter isotopes. And it's not only looking for one evidence. If you find one evidence for life, you cannot claim that you have found life. You need a line of evidence. You need to have a context favorable. You need to know that the place was habitable in the past or in the present. And you also need to find all this kind of evidence all together. Okay, so that's very general for looking for life anywhere in the solar system, or so mostly in the solar system. But let's go to Mars. So there were many, many missions, orbiter, landers from the past 20 years, and it will continue in the future. And I will mainly focus on the Curiosity rover that François mentioned, and also on the ExoMars rover if I have time at the end of the conference. And this is the second part of the ExoMars, the first part being the TGO that François mentioned that looked for atmosphere, methane, and potentially organic molecules. I didn't know about that, but I'm not really confident that it's feasible. And so I'm starting by the Curiosity rover, and you can see that the first part of the exploration is to look for habitability, and more we are looking for actual signs of life. And the Curiosity rover, something really cool about that is that it landed in Gale crater, and Gale crater is between 3.5 and 3.8 billion years old. And if you look, the equivalent on the Earth, 3.8 billion years is when you had the emergence of life. Just after the late heavy bombardment, as soon as the Earth became habitable, life appeared on the Earth. And so we're looking on Mars at the same age crater than the age of when life appeared on the Earth, which is pretty positive because when the conditions were very similar between Mars and the Earth, and if life appeared on the Earth, why not on Mars at the same time? So we're looking at this time in history. Curiosity rover, it's an international collaboration, because in this kind of mission, if you don't have an international collaboration and collaboration in general, you cannot achieve anything. And USA, France, Canada, and all these countries are involved. And the main point for Curiosity is to look for habitability. It's not looking for signs of life. But you will see in the following slide that one of the instruments can have some clues for looking for biosignatures in addition to the general goal of the Curiosity rover to look for habitability in general. So it launched in 2011, landed in 2012, and it has been very successful since then. It's 100 kilograms or 80 kilograms of scientific payload, and so it's 10 instruments, very big rover with a lot of investigations. It landed right south of the equator. We're very far from the poles that François was discussing for water. And so, as François already said, there are some stratification and with a clay layer, sulfate layer. So we're very interested because there are different minerals and that's the context, and this context can be very cool for preserving organic molecules that we're looking for. Curiosity rover has remote sensing instruments, so 10 instruments total, contact science instrument, environmental sensor, and analytical labs. I'm going to discuss only one of these instruments where I'm involved with the sample analysis at Mars, the SAM instrument, which is in the body of the rover. It's the most complex instrument that has ever been sent to another planet, for now. And it's the size of a big microwave. It has 3 subsystems in the SAM instruments. One of the subsystems is a gas chromatograph, that the 6 chromatographic columns that you see here, which are French and made in the French labs. The mass spectrometer, which is made at NASA Goddard, and the tunable laser spectrometer to look for methane and isotopes, which is made at JPL in California. And so SAM is able to analyze both atmospheric samples, solid samples from the arm of the rover, and can do really a bunch of different types of analysis. And one of them is to look for methane in the atmosphere. And one of the big results is that, so you see on the map here, it's the driving path that the Curiosity rover took from the south actually to the north. It's inverted. And the mission sols, so the Martian days, and all along the path we took some atmospheric samples to measure the methane. And at one point in the path, so here the yellow square, there is like a burst of methane which is well above background and which cannot be reproduced later, which has not been reproduced later actually, and which is above background, so we know it's a signal, and we do not know where it comes from. So all the different words that you see here, it's all the correlation we try to find for the correlation. Why do we have methane here? Can it come from contamination from the rover? Was there at a place where the wind had a different orientation? Can it come from the rover, the season, the meteorite showers that we can observe on Mars that could bring some methane? And can it come from UV radiation? If you have more UV radiation, can you release some methane from the soil? And we could not find any correlation with any of these parameters that we've looked for. So there is one burst of methane that appeared at one point in the Curiosity traverse, and we do not know where it comes from. Why at this point in time we had this burst of methane? So where it can come from, I won't talk about that in general, but it's just that you can have geological source of methane, or you can have biological source of methane. On the Earth, most of the methane is from biology. That's why we're very interested in the methane. And then the methane can be just trapped in a clatrate and can outcast for one reason or another if the temperature is higher, but we couldn't find any correlation anyway. So we do know that this is happening. We have one burst of methane, like really sporadic in time, but we have no idea on the origin of the methane, obviously. We cannot rule out the fact that it can be from microbes, but there is no indication for that. Okay, so the other type of analysis that we do with the SAM instrument is the solid samples. It can drill, and the video that François showed was about this drill, and it can scoop some samples. And this is one of the drill. It's very small, 1.6 centimeter wide, so it's just a close-up, so it looks way bigger. We always test the durity, solidity of the rock first. No? Hardness? I don't know. I think there is a specific term in geology. And so with a mini drill, and then we do a full drill. So right now we have issues with the drill, but it's soon to be resolved, and we will soon have some more samples. And so this is, and you can see something very interesting is that all the surface is very red, and when you drill, it's gray. So the oxidation layer is really at the top, and as soon as you drill, even just a little bit, you reach some non-oxidized samples. We've done a lot of different drills during our traverse. So this is the traverse. It's, I think, 12 kilometers to date or something like that. A lot of drills, not all of them we've analyzed with SAM, because there are other instruments that analyze the drilled samples. And the two that I will focus on are the Cumberland sample, which is the second drill only, but the most interested, because also we stayed at this place for months, so we had many sub-samples, and we have statistics on this sample. And also the Mojave sample that has other interesting features, but Cumberland is the one that I'm going to really focus on. So you can see the selfie that we like to take selfie at each drill spot. And the size of the drill is very small compared to the Rover. It's not a close-up this time. Cumberland. It's floor sediment. It's the floor sediments from the Gale crater. It's the first drill site analyzed by SAM. Actually, the first drill was John Klein, and the second was a few meters away, Cumberland, but it's very different geological settings. And it was a lake deposit. So we are at the bottom of a lake. There are sediments at the bottom of a former lake 3.5 billion years ago. So very interesting. And why are we looking at so why we're looking for organic molecules? It's because, as I told you, they can be degradation products of living organisms, and they are also essential for habitability or food for life, building blocks. And from chemistry to biology, you see a complexification of molecules, from simple primordial molecule, so very chemistry-like, to biological molecules, proteins or hopanoids or DNA. So if you find this kind of molecule, you know that you found life. If you find this kind of molecule, you kind of know that you find chemistry. And if you find this intermediate side of molecule, amino acids or some complex carboxylic acids, you need to investigate more and to look for these signs, like the distribution with the number of carbon, of the chirality of the molecules, to know if it's a degradation product from life or if it's complexification from chemistry. But they're very interesting, all of them anyway, and organic matter, it's a criteria for habitability, so that's why we're looking for the whole range of molecules, from simple to complex, to know if the place was habitable and if possibly we had some life at this place. The SAM instrument is very complex, but one of the way to look for organic molecules is so that's a pass in purple. You have a sample which is 50 to 150 milligram that you heat from ambient temperature to 900. When you heat the sample, you release the molecules that are trapped in the sample. And then there is a trap to concentrate the molecules. And when you hit the trap, you release all the molecules at once that you send at the entrance of the gas chromatograph, the French part of the SAM instrument. And then you analyze that in a mass spectrometer. So you have GCMS, gas chromatograph converted to mass spectrometry, which separates molecules from a complex mixture, because complex mixture you cannot identify anything. And when you have separated these molecules, you identify them in the MS. So that's a very simplified version, because a real life version is that. And I do not show it only because it's cool, but also to show that SAM is very, very versatile. You can choose whatever you want to do. And SAM has been able to make some new experiments that were designed during the mission that were not initially planned, but that we decided to change the valves and the path and the gas path, anything, and to make some new experiments. So it's a cool instrument. Just a quick video to show you how the GCMS works. So it's a
instrument permettant ces analyses, SAM et ChemCam joue un rôle essentiel à la mission MSL. SAM,
we don't care about the
analyse l'atmosphère et le sol martien.
So this is a SAM
Pour cela,
instrument.
SAM utilise deux méthodes, la chromatographie en phase gazeuse et la spectrométrie de masse. Les échantillons de poudre de roche prélevés sont chauffés à 250 degrés
to 150 milligrams that we drop in an oven. The oven is heated to 900 degrees to release the molecules. And then the gas chromatograph is called gas chromatograph because you have helium gas flushing the molecules to the GC column. And the GC column will separate the molecules
un instrument qui permet de les peser.
Depending on their
Le temps de
mass,
parcours des molécules
and then it will create a chromatogram where each peak is one type of molecule, and with the mass spectrometer you will identify each of these peaks as being this molecule.
Atomique de la roche et permet de connaître sa nature et celle des sols autour de Curiosity. Son laser peut viser.
So it's supposed to be really simple, right? You have one chromatogram, each peak is one molecule, you identify it, and bingo, you find your molecule. But that's what it looks like in reality. So it's not only one peak. There are many peaks, many mass, many background, many everything. That even the background, you see it's different. It can be high, it can be low, and you cannot really see peaks in that. So that's our main work, is to crunch this data to find a molecule. And it's also, again, there is a point of showing you this kind of image, is to show that in space science, you find what you look for. You cannot just be blindly look at that and say, hey, what's in there? You have to specifically search for one molecule to find it in this data. And so that's why it can take time, and that's why you really need to understand what's going on the Earth to look for specific molecule that you're interested in. And so from that to that, it took about 2 years. And this is the first detection of organic molecules on Mars, published in 2015. And the molecules are shown here. Those are Martian molecules. Actually, those are Martian carbon. In gray, it's the carbon, and Martian chlorine in green. But the molecule itself, even if they were detected as such, we are 100% sure about the identification, but we are not sure that they were present as such on Mars, because we heat the sample to 900 degrees, so we make some new chemistry. And because our perchlorate on Mars, it's full of chlorine, so you will chlorinate your molecule. It's possible that the initial molecules present in the Mars sample were much more complex, non-chlorinated molecules, and in the SAM oven we add this chlorine, and at the end we observe these dichloroalkanes and chlorobenzene molecule. So that's what guides us for lab experiments to go back to the precursor of these molecules, potential precursor, because we cannot be sure. And this is what type of experiment. So I would say that 50% at least of our work is to work in the lab to understand what's going on Mars. And the other 50% is to try to work on Mars data and to decipher what's going on Mars. And the type of lab experiment we do is to this experiment was to extract all the organic content of the Murchison meteorite, because we know that meteorites, they arrive on Mars and they should deposit some molecules. So the type of molecules that are present on meteorites, there are the type of molecules that we would expect on Mars. And so we extract the organic molecules of the Murchison meteorite, which is one of the most famous ones because it's full of organics with amino acids, but all from chemistry. And we made a SAM-like experiment. We heated the sample with perchlorate to 900 degrees. And what's interesting is that what do you see when you do that at the green bar here? You see the chlorobenzene and dichloroalkanes, which means that the organic content from Murchison meteorites are good candidates as precursor of the molecules that we observe on SAM. And then there are other experiments with phthalic acid, benzoic acid, or mellitic acid, so non-chlorinated carboxylic aromatic organics that are in presence of perchlorate, and you heat them and you would observe an increase in the chlorobenzene detection. So they are good precursor as for the chlorobenzene that we observed on Mars. So at the same, but with more visual. So basically, when you have a non-functionalized aromatic molecule, you will not create some chlorobenzene. When you have functionalized with either carboxylic acid or alcohols, so here you have the phthalic acid, the benzoic acid, and the mellitic acid, you will form all state of chlorinated aromatics, including the chlorobenzene. And what's even more interesting is that mellitic acid has been described by Benner in 2000 as being the most metastable molecules, degradation product of the molecule at the surface of Mars. Basically, he said that if there is life on Mars, they will degrade in some different types of molecules, and these degradation products would be mellitic acid as being the most metastable product. That's the one that would stay the longest at the surface of Mars, and that we would be the most likely to find. And it can be also from chemistry, but he cites the example of biology as well. And so basically, it's a very good candidate as being at the origin of the chlorobenzene that we detect with SAM. And so when we showed that, people were like, oh, okay, so you find chlorobenzene when you pyrolyze mellitic acid with perchlorate, but you also have dichlorobenzene and trichlorobenzene, so why don't you see them on SAM? So we went back to the data, and actually we found them. And because, again, we have to look specifically for something to find it. And we looked specifically for dichlorobenzene, and we find dichlorobenzene on SAM. And most importantly, we find 2 isomers, maybe 3 actually, of dichlorobenzene, so which is very cool. It means that our GC columns are able to separate the isomers of some molecules. And then a big part of the work is to confirm that it's really that with lab runs. So we run in the lab with a SAM spare that we have in the labs. We run some compounds that we think are them, and then we make the correlation with the retention time. So this is the retention time. Actually, I didn't mention that, but it's the time that on a chromatogram, this is the time the molecule spent in the columns before being eluted at the end of the column to be analyzed in mass spec. And so retention time in the same condition should be always the same. And so we explain why there is a little shift, but we confirm from lab runs that those are molecules that we found are dichlorobenzene and also this trichlorinated molecule. So this is a paper that was just submitted by Cyril Zopa, a colleague from LatMOS. And so you can see that it's just submitted this year, or 2018, and the data are back from 2014, so 4 years to understand that we have dichlorobenzene. And I did not have any slide on that, but what's very cool also work that we start to do in the lab is to look back for chlorobenzene and dichlorobenzene and all this stuff in the Viking data dating from 1976, and actually we found the chlorobenzene. So we find a new molecule from a data that is 40 years old. And now we try to have the same type of lab run in the lab, so we try to recreate the Viking columns. Unfortunately, it's not referenced in the literature, and all the people that worked on that, they are either senile or dead, so it's really hard to get information from them. And the information in the literature, they're wrong, usually, because they say, okay, so this is what we're going to do for the GC column for Viking, and then at the end of the paper, you have, but it's not the one which was used for the flight. and we have no idea on the one which was used for flight. So that's really, really interesting to see that there are a lot of data, and the more eyes we have on the data, the more likely we are to find things. So the organic molecules, they were found in, so this is from another instrument. From some, all of them work in concert, which is really cool. And the Cumberland sample has 20% of smectite. It's a clay, and clay minerals, that's a series of layers, as you can see, and in between the layers, you can first accumulate the molecules and then protect them over time, over geological time. So clays are very, very good candidates for preservation, long-term preservation of organic molecules. And it's the sample where we had the most clays where we found the organics on Mars. So it's a good candidate for any future analysis on Mars. If you have clays, you want to look for organic molecules because they're more likely to be preserved. Okay, so done with the organics, and Sam does not do only organics, but also looking at isotopic ratio. And for example, isotopic ratio, so I told you they're really interesting in terms of biomarkers or biosignature because life uses lighter isotopes. And one of them is the sulfur. And so they are used for other things also, and atmospheric loss, and because you lose mostly the lighter isotopes. So if you have an enrichment in heavier isotopes, you can backtrack and calculate the loss in atmosphere, and so the initial atmosphere that you had on Mars. But here we focus on the biomarkers, like the signature of isotopes that can be from life. So this is a stratigraphic composition of Curiosity, because Curiosity is a climber. François told you that it's climbing the central mount of the Gale crater. And so we can have some stratigraphic figures that I don't understand, I have to admit, but stratigraphers do. And so we have Cumberland sample, this one, that was at the base in the Yellowknife Bay at the really beginning of the mission before starting the climb. And then we have other drilled sample where we analyzed the isotopes. So here in red are the isotopes of sulfur, and you see that they are all like really close to the average. And Cumberland sample is really specific, and we have other drilled samples now, and they are all close to the average. But Cumberland sample is very, very specific, very light in sulfur. And we have no explanation for that. One of the explanations is that it can be from life. It doesn't mean that I don't say that there is life there, but it's just that life is a potential explanation for a light isotope at Cumberland. So that's the conclusion here. The biomarkers cannot be ruled out, but it doesn't say that it's that. We also have nitrate on Mars. We detected with the SAM instrument still NO and from solid samples, and it has been backtracked, and the NO comes from nitrates. And nitrates are food for life on the Earth. They are mostly, it's like methane. When you see nitrates on the Earth, it's really related to life. And we have this nitrate in a form that can be fixed by life, and that's biologically available. And at Cumberland. Again, still the same sample, very interesting. So I won't go into the details of the nitrates, and but the conclusion of the nitrate is that no, I won't go into that. But we look at the difference between nitrates and perchlorates, and on the Earth, it gives the biology versus abiotic sample when you look at the nitrates to perchlorate ratio. And so, again, for the nitrate, it's not excluded that it can be from life. So everything in Cumberland is really pointing towards it's not incompatible with life elements. So the next step is to look for more complex molecules, because for now we just have some simple organics. So that's why we have derivatization on board. The derivatization is a process that preserves chemical structure, make them more volatile, and you can analyze them in GCMS. For example, amino acids. Amino acids, you could not analyze them in pyrolysis GCMS, as I showed before. You need to add a derivatization region, some wet chemistry, to be able to see those molecules in this instrumentation. And that's an Earth example, just from an analog from Antarctica, just to show you the difference between the type of molecules that you can see in pyrolysis GCMS, just when you hit the sample and send the volatiles to GCMS, or with derivatization GCMS. And it's basically only aromatic, simple molecules with pyrolysis, because you break them down. And with derivatization, you can see much more complex molecule. Here on this Antarctic sample, I found some derivatized phosphate, which is from degradation from DNA, and amino acids, and all these kind of molecules. And most of the peaks, there are molecules, but it's very, very hard to identify them, because when you derivatize a molecule, you change the molecule, and then it's not in the mass spec library anymore. So you have to look to, again, to know what you're looking for, you search for this molecule, you derivatize them in the lab, and then you see if it's the same mass spec than the one that you found. So even for Earth analog, it's very, very hard to identify the molecules. So the derivatization, my PhD advisor, actually, Arnaud Buch, made this really cool scheme that is used in all presentations now, even from people that we don't know. And that's non-volatile molecules, such as amino acid. They would be like this little caterpillar. And when you add the derivatization reagent, you make them a butterfly. And caterpillars are not able to fly to go to the GCMS and to be analyzed. But obviously, butterflies can fly and be analyzed in GCMS. And that's the more scientific reaction. And on an amino acid, for example, and as you see, this is the part, this third butyl dimethylsilyl group here, what we call TBDMS, that you add to all the labile hydrogen of the amino acid, so the OH part and the amine part, and you make a molecule which is way bigger, but more volatile, because there is no hydrogen that can make these hydrogen links and prevent them to be analyzed in GCMS. But this molecule, then, it's not in the MS library anymore, so it's very, very hard to identify them, and we need some lab runs to be able to identify them. And the target compounds for this derivatization are all these prebiotic molecules, the ones that can be from complex chemical complexification, or that can be from the life degradation products. Derivatization in SAM, it's in different cups that we have, so that's the carousel that holds the different cups. There are 74 of them, and amongst the 74, 7 of them are with MTBSTFA, and so you can see here all the quartz cups, they are open and they just receive a sample for pyrolysis, and you see the metal cups that holds derivatization, and they need to be punctured, and then we drop the sample in the liquid, and we heat the sample to perform the chemical reaction, and then we analyze the chemical reaction products in GCMS. And one of them is leaking, and so we have some background of MTBSTF everywhere in SAM. It's cool. Now we understand how to work around it. And this is a result of derivatization that we've run. So we've run 2 types of derivatization, and this is a result of the first type, because the other one is really recent and we're not allowed to share it yet. And so the first step is that we've used the leak to perform a derivatization. We've took this leak and send it to the sample and then perform opportunistic derivatization. And this is the results from the opportunistic derivatization on Cumberland again, because we like really much Cumberland. And we can see that there are some high masses. So M over Z is mass spec masses, which is the mass of the molecule, and that's much higher than any other masses that we've observed before. So there are some molecules. We tentatively identified them. It's very hard, again, because we need to confirm with lab runs and the retention time of the chromatographic columns and the mass spec and other parameters. And one possibility for this peak that you see is the benzocarboxylates, so benzocarboxylic acid, which is the type of molecule, when you heat it in presence of perchlorate in pyrolysis GCMS, you form chlorobenzene. So everything correlates. And we have another type of molecule that maybe also, but maybe not. And it would be a long-chain carboxylic acid that we've identified at mass, can't remember the mass here, but it was a high mass, and so 131. So we identified it only by mass, but it doesn't match with the retention time. So we are very not sure that it can be this type of molecules. But so that's the type of analysis that we do. And the other derivatizing region that we have on SAM is it's actually a thermochemolysis more than a derivatization, but it's still a derivatization. And it means that we use the chemical to perform derivatization under high temperature. So that's why it's thermochemolysis. And TMAH, so the derivatization thermochemolysis region that is present on SAM, and that we have only 2 cups of it, and we haven't used one of them yet, but we're preparing the run. They are targeting carboxylic acids, which can be degradation products of fatty acids. So again, life. And so that's what I explained at the first slide, that in life we will have only compounds which has an even number of carbon compared to chemistry, where we have even and odd number of carbons in molecules distributed in a Gaussian. So this derivatization will be used on SAM and may lead to this kind of analysis, which would be cool. And last thing about SAM is the CO2 release. And so I don't ask you to read all of this. It's just a figure here that the CO2 release along the temperature range of the sample heating. And the CO2 release is very high, and we cannot attribute it to carbonate or other either organic or inorganic carbon. So we don't know where this really high CO2 comes from. It may be from combustion of organics, because we have perchlorates. Perchlorates release O2, and when you heat an organic in presence of O2, you will oxidize it and form CO2. So that's maybe the reason why we see so few organics on Mars with Curiosity, and that's maybe the reason why we see so much CO2. And if all the CO2 comes from organic carbons from organic molecules, we would have hundreds of ppm of molecules present in the different samples, including Cumberland. So what's next with Curiosity? Right now we are in the hematite ridge, the Vera Rubin ridge, or VRR, and we are going to climb to the clay unit and then to the sulfate unit. So it should be in the next 3 years. And as I said, Curiosity is a climber, so that's the difference of elevation that we're going to climb to the end, to the sulfate unit. And we're actually, currently we are midway to the highest altitude that we're going to. And sulfate, so clays, I showed you that it was very interesting for preserving molecules, but sulfate is also very interesting for preserving molecules, and on the Earth, some very billion years organics have been preserved in some kind of sulfate, so that's why we are also very interested in sulfate. And just a picture, because it's really cool to see the kind of quality of pictures that we can obtain from Mount Sharp, from Mars. Okay, so oh yeah, during when we're bored, we do some background check, so checking the holes on the wheels. So this is not normal, and also we take pictures. So that's not us, but we look for us in the high-rise pictures, and you can see the rover here, the Curiosity rover, and all the tracks. Yeah, so it's cool. And each time we're at a drilling site, we take a selfie. So we have all these kind of selfies. They kind of all look alike, but it's still fun. So for Curiosity, the conclusion is that Mars was habitable in the past. This was Gale Crater. It was a lake full of fresh water. And 3.5 to 3.8 billion years ago, Gale Crater was habitable. We found all the possible criteria for habitability. And now we're looking for much more complex molecules. We found the primordial molecules. It's in French also. We found them. And so now with SAM, we will be able to find these kind of molecules. We will not be able to find biological molecules. And so that's the conclusion of the first part, but then I want to, I still have some time to discuss then the field work that is so important in our work, and it's mostly pictures. So. And we have different, so we've seen burst of methane, which suggests a hyperlocal source because it was one burst. We've seen light sulfur isotope, so fractionation towards light isotopes. We've seen presence of nitrates and high abundance of CO2 that can be from organic carbon, simple organic molecules, more complex molecules that are seen with the derivatization and that are currently trying to be identified. So the results are not compatible with life, but they are not incompatible with life. And curiosity has only the potential to detect habitability. However, SAM has a little bit more potential to look a little bit for biosignature, but it's not meant to do that. So we're not going to find life with curiosity. We need more things. But SAM will help to take lessons for feeding forward the future experiments, notably the MoMA experiments on the ExoMars rover, and to select the samples that should be brought back on the Earth, or which has the most potential for biosignature, etc., etc. So the second part is what we do, and it's a big part, and it's very important, is lab work and field work, because we have in the labs, we have different types of instruments and with different fidelity from the SAM instruments. This is the SAM testbed, which is SAM-BIS. It's the exact same instrument. It's at NASA Goddard, and it's used to perform science and also to prepare all the runs, to be sure that there won't be any crash when we write a new script to send to SAM. So this is very useful, and it's very similar. It's the same instrument that SAM. Then, so this is the instrument that has been opened for reparation recently. And then we have some sub-parts of the instrument. So this one is at LatMOS. It's because the GC was made in France. So we have a GC breadboard, and we use it to find the retention time of our compounds and to understand the results that we obtain on Mars and to give a sense to them. And then we also have this kind of breadboard that are less representative. It's between the lab run and the SAM run, but it's very informative. And then we have the lab instrumentation. So we really have these 4 different levels of fidelity that we use for very different purposes, but that are all essential to understand Mars data. And why we are interested in, what do we run in these instruments? We run Mars analogs because we want to understand what's going on with perchlorates, or when you have sulfates, because sulfates, so they can be good preservation, when you have clays. So you mix all of that, you find Mars analog on the Earth, you mix all of that with organic molecules, perchlorates, and whatever you want to represent Mars. So you are taking Mars data, putting that in lab data, and then looking for the results from this lab data to understand the Mars data. So it's really a cycle between Mars and the Earth. So we have this really high necessity for investigation Mars analog samples. So this is just in French a bunch of analogs that I'm using as Mars analogs. It can be as simple as you go to the park next door and you take some dirt and you have a lot of organics, or you need to go to more isolated places that are similar to Mars in this point or this point, like either because you have few rainfalls, like the Atacama Desert, or because you have some oxidation. And here it's Svalbard in Norway, and we went there on an expedition called Amaze for some Mars analog Svalbard expedition. I can't remember the first A. And we were on a ship, on a research vessel, and we spent 2 weeks with instruments that are representative of what's on MSL and what's on ExoMars to see if with those instruments we can find life in Svalbard. Because if with the instrument you cannot find life where you know there is life, there is no chance you'll find life on Mars. So that's what we've done, and so just the Lensé was our research vessel. It was it stayed in the middle of the fjords, and we had this small Zodiac to go to collect samples. And in a couple of days after collection of the sample, we had to identify everything that was in the sample from a geological point of view, from an organics point of view, and so using only instruments that are on board Curiosity and ExoMars. That was my lab, and in a day you have to make a lab, you have to chain everything because you have waves. And actually here we have the MoMA chromatograph. That was the first coupling between the MoMA chromatograph and commercial MS. So it was really hard to, because it was a GCMS, this one was a whole system, and I had to remove half of it and to make it work with the MoMA GC, so it was kind of a pain, but very, very interesting. So this was our lab in the Svalbard, and this was a sample collection. We had to climb hills to go to places that were tracked first as potential interest for Mars exploration. And so this place in particular, it was very similar to one of the Martian meteorites in terms of mineralogy. So that's why we went to this place for analysis. And then you collect the samples and you do the analysis in the lab. So it's a close-up of the MoMA GC coupled to the commercial mass spectrometer. And you can see MoMA PI here, Fred Guzman, working on the sample. And so that was interesting in that sense that we've analyzed different types of sample, and you see the GCMS runs of these different types of samples. This is a blank at the top. And here it's a sample where just from the organics distribution, you can see that there was life, but life is not present anymore. It's carboxylic acid, there is no amino acid, there is no DNA byproducts or whatever. It's only molecules that are very resistant, but coming from life. So life was present in this sample, but is not anymore. And on this sample, you can see amino acids, you can see byproducts of DNA and all kinds of carboxylic acids. So on this sample, there is life. So just by the distribution of organic molecules, you can see if there is present life, past life, or no life. So that's with all the instruments we do have on ExoMars and on Curiosity. So with those instruments, we are able to find a potential life on Mars if there is some. So that was a paper of comparison of the MoMA. And so we had polar bears. So he was our guide to protect us from the polar bear, because that's one of the only animals that will attack you and not run away. So it's very dangerous. And we also had some rescue operations. There were airboats that they went to the ice sheet and they did not expect to use so much fuel, and so they ran out of fuel in the middle of the ice sheet. So we had to go there and to give them some fuel to get back to the shore. It was really cool. So we had an icebreaker boat, obviously. And at the end, we always pose in Men in Black. So the whole team is posing as a Men in Black. And this is the gun I'm holding is to shoot bears. So. Okay, so I think I will end here, or just one slide about ExoMars and MoMA, because so I have a whole discussion that I could do, but I just want to present this slide for MoMA and ExoMars, which are the improvements that MoMA has over SAM to detect potential biosignatures. First, the ExoMars rover will drill down to 2 meters deep in Mars soil, and 2 meters is basically the penetration depth of the radiation that are very destructive to organic molecules. So we will be protected from all the radiation, and we can reach some samples that are protected from degradation. So probably a whole lot more of organics. Maybe there won't be any perchlorates at this depth. We have no idea. And that would be cool, because perchlorates are a pain to deal with. And then, and the sample the Camelon sample we've analyzed on SAM, actually, it has been dated as being only 80 million years of exposure to radiation. So we were very, very lucky to find a sample that was really recently exposed. So it means that there were a very high erosion rate and that the sample was exposed for only 80 million years. Even if the crater is 3.5 billion years. And that's probably why we found all these organics only in this Cumberland sample, because it was only recently exposed. And by drilling down to 2 meters, we do not have to be lucky to find a recently exposed sample, because all of them won't be exposed at all. The other thing is the derivatization, so still the same figure here, but with a different derivatization reagent that will allow to detect the chirality of the molecule. So with the DMF-DMA derivatization reagent on board MoMA, there will be possibility of seeing an enantiomeric excess, so the left and right form, and if we find some amino acids, we may be able to find an excess of the L form or D form of amino acid to have more insights on the origin of this amino acid, biological or abiotic. And then there is an additional experiment, which is a laser desorption ionization, that shoots a laser on a rock or sample, and this laser has enough energy to extract the molecules that are present without destroying them. And then these molecules are stuck in the mass spec for an analysis, and we can reach very, very complex molecules with this technique. So we will reach the whole range of simple to complex molecules down to 2 meters deep and look for an enantiomeric excess. This is all we need for potential detection of biosignatures of Mars. And with that, I will take any question you have.
Thank you, Caroline. Well, for a question, we're going to have to take only 2 and then pass to our next presentation. So, some questions?
Jamais de questions en chimie.
Okay. Just for information, there will not be able to make a coffee break, and we'll pass to our next presentation. Francis Rocard, who is going to give us some information about the possibility of life or sending some people on Mars.
So I have 45 minutes to present Men on Mars, which will take 45 years. So 1 minute per year, it's a challenge. So until June 14, it was impossible to present such things. In June 14th, the National Research Council published a report, which is on the web. You can download this report. It's a PDF. And all is inside. So all what I will say is roughly coming from this report. The report is named Pathway to Exploration, Rationale and Approach for US Space Program of Human Space Exploration. I will explain what means pathway, which is a key word on the title. Just to remind, this the National Research Council is not NASA is depending on Congress, and it's what is called the NASA Authorization Act, which is a law in 2010 that pushed NASA to set up this working group. And they spent 2 years to really understand what the Congress wants, so that's a joke, but it's a reality. And they study during 2 years, 130 guys, experts, was involved, and all the names are in the report. And as I write in French, first very full detail of such endeavor to send men to Mars, because all what is studied in the US, nothing in France, a little bit at ESA, but the state of the art is in the US. There is one chapter, more than 20 pages. This chapter is why. And this is what we call in French élément de langage. So it's what's the reason why the US president will decide to send men on Mars. And when journalists will ask, so why do you decide this? This is the answer. This is a tentative answer. And the answer is not simple. So they go through all the argument. Maybe it's an economic aspect. the answer is there is absolutely no way to win money when you go to Mars. You will only lose money. You will not win money. Is it a national security aspect? The answer is no. Is there argument on international relations? Yes, of course. It's a soft power. There is some geopolitical benefits, but it's one spin-off of this. Same thing on the ISS when the US gather partners with ESA, with Japan and Russia, and exclude China, as you know. There is also education and inspiration, which is typically a US argument, but that's a real argument. Even those human and robotic spaceflight are also a very good argument for education and inspiration. And there is science. So is there really an argument for scientific argument to send men on Mars? And the one key argument is to, sorry, I'm reading what is written because I don't remember exactly. Anyway, so the science is not really a big argument. And today, the robots do something very, very nice. And what we see with Curiosity is the state of the art of what we can do on Mars. But remember that the question needs to be valid during 40 years. So the key argument is that today, men do better than the robot. But 40 years in the future, we don't know if the robot will be not more efficient and less costly than human. So the argument humans-robot is today is something, but tomorrow could be different. So the argument of the man doing better than the robot is valid today, but not really tomorrow. And then they go through the survival. Elon Musk is very in favor of this and say Mars is a plan B. So we will destroy our planet and then we will go to Mars. So it's nice activity. I don't share this point of view, and also share human destiny and aspiration, which is to do something nice. And when, for example, when this question was asked to Hubert Curien, which was Minister of Science, President of CNES, the answer was, "Oh, we will go for the fun," which is something exactly what he said. Because this enduring question, this means the question whether the answer should be valid during 40 years, is the answer by question, so which is tricky. And the idea is to demonstrate how far from Earth can human go, and what is more curious is that the answer, what can human discover and achieve when they get there? This means today we don't know. We don't know what can human do when they will be there. So you see, the argument why is not a simple question, and obviously it's not science. I'm sure you understand this point. And so there is no single rationale alone to justify the value, and there is a keynote. The level of public entry in space exploration is modest. There is a lot of poll in the report, and we see that even if there is a global consensus at White House, Congress, NASA to say the big future is a man on Mars, but the Americans, they don't care. They don't care. The polls say there is 20% or 15% to say, yes, we want to go to Mars. The others, they don't care. So, and the public is probably more attracted by economic issue, education, medical or scientific discovery. So this is peculiar. And so one aspect of the report is what is the limit of our reflection? So they put this limit. They say that we don't go beyond this moon, asteroid, Mars, and moon of Mars exploration, beyond, which means interstellar, which means we want to go to Europa. So they don't, they limit the frame of the reflection. And so the horizon goal is to send men to Mars. And as I said, there is, and it's very peculiar in the US, there is a real consensus. So everybody is agreed, NASA, Congress, White House. The 21st century will be the American on Mars. So no, the question is how we do that. Yes, how we do that, and one aspect is that the if we imagine that the budget of NASA will increase only by inflation, the answer is no. It's impossible. So we will have to ask Congress to increase more than inflation the budget of NASA. Just to compare, when Kennedy makes his big speech in May '61, saying we would man on the moon, in '65, the budget of NASA was multiplied by 50. So NASA was nothing in 51, in 61, and in 65, $25 billion of budget, annual budget. So it was a huge increase in the NASA budget. It will not happen here. This hypothesis of the expert to say we will not request to double the NASA budget in 2 or 3 years. It's impossible. The Congress will say no. So the idea of pathway is what has been done for the moon is to do all in parallel with a huge increase of budget. It's impossible for Mars. We will do that in serial. This is why we need pathway. Pathway means we need to go somewhere and to the moon, to the asteroid, to the Mars orbit, to I don't know. And with this pathway, each time we will develop the key elements to, at the end, will permit to go to Mars. That's the idea of this. And also, there is absolutely no perspective of positive economic return. So, if you want to, if people think that we will win money sending men to Mars, it's a lie. It will absolutely impossible to win money with that. We will only spend money. And the end, as I said before, it's not a big priority for the Americans. And about international cooperation, the expert, it's not politics people here, it's only the experts. They said the good way to save money for the US is to have a big partner. Minor partner, but a big partner. This means 49% is the best. This means the US are the leaders and we have a big partner. Who can be these big partners? China, obviously. In terms of capability, in terms of technology, in terms of what they are doing now, they are putting men in low Earth orbit, they are landing on the moon, they will do sample return from the moon, and they will send Taikonaut to the moon in 2036. It's written, it's said by the China's people. China is the best partner. This is why you have seen The Martian, Seul sur Mars? So, who saves the American? The Chinese. So, it's the same thing. And, but in terms of politics, it's impossible. The politics today, Congress say no cooperation with China. It's written in the law. There is ITAR issue. Nothing can be done with China today. And I think with Trump, it's not so good presently. So, just a word about ESA. ESA is today, the ratio on the spending between ESA and NASA is 15. This means when the US spend 9 billion a year, we spend 600 million a year. So this is 15. So we are a very low partner. We will be there, but at very low level. And one consequence is what Zubrin said. Zubrin is president of the Mars Society in the US. This is what Zubrin wants to do. It's Mars Direct. Wait, let's go, like to the moon. It's impossible. So they say, forget it. Forget it. This chain will not happen. And this chain will be the pathway. And so the experts do not decide which pathway we have to be done, but they say there is different pathway. So we are here, we are on the ISS, low Earth orbit. We want to go there on Mars surface. What will be the pathway to go there? And this is a political decision to decide the next step. This one, this one, this one. And it has been done. And at the end, probably will we go through Phobos, but also we'll go to Mars orbit before Mars surface. And for example, at the time of this report, this was the asteroid redirect mission, and this is cancelled today. So things change quite rapidly in that domain. And again, in terms of pathway, you can do from IRM, but this one is dead, up to Mars surface, through Martian moon, or you can go to lunar surface, sortie. Alors, sortie is Apollo. Sortie is Apollo. But when you go to outpost, mean long-term base on the surface. So that's the terminology. So this is Apollo, this is a long-term base on the moon and then on Mars. And the reality of what will happen is not here. There is another possibility I will show you. Just to understand the difficulty in terms of delta V. When you make rocket science, delta V is the key parameter. It's the size of the rocket. This means when you're in space and you want to go somewhere, you have to accelerate. You have to turn on the motor, you move, and then you have to turn again the motor to decrease your velocity. So you have delta V. And the low Earth orbit is, we know the rocket do 7, 8, 9 kilometers per second. This is a rocket that do that. But if you want to go to the moon, for example, you have to go to roughly 20 kilometers. You have to double, more than double. For example, the Mars flyby, which is very simple, this means you go to Mars, you take a picture, but you don't stop, and you go back to the Earth. And this is low. This is 14. This is less than the moon. If you want to go to asteroid is all this blue one. There is a lot of asteroids. Some asteroids are low delta V, let's say 14 or something. There are not a lot, but there is some. But you can have asteroid here at around 30. 30 is huge. I don't know one mission that has 30 kilometers per second of delta V. It doesn't exist today. So it's absolutely a lot. And if you remember the Martian is here. So if you want to stay 30 days, you have, let's say, 17 kilometers per second. But if you want to stay 500 days, it's less. So it's more interesting. And at the end, if you want to spend $200, $300, $400 billion, of course you will want to do that. You want to stay on Mars surface. No, this is Mars orbit. You have to compare this one to this one for the surface. It's the same thing. And but if you want to reduce the duration, this is the duration: 200 days, 400, 600, 800. So if you stay only 30 days, it's quite low. If you want to make a very short stay, it increases drastically the delta V. So it's not manageable. But at the end, I'm sure this will happen. Finally, this will happen. Because what you want at the end is this. It's not to stay 30 days and spend 400 billions. And this is to illustrate the normal Oman transfer, what we call the Oman transfer. The Oman transfer is a way to go from one point to another, one planet to another, with minimize the energy. So this is an Oman transfer. I don't see my slide. So you go from the Earth and you go to Mars. This is a real Oman transfer. You go half a turn. You stay 500 days and you make half a turn to come back. This is the normal way. This is the window for launch at the beginning and at the end. If you want to make a short stay, the one way is good at the beginning, but the return is not good because you have to go through Venus, and it's a 400. This is Venus, and you have to 400 duration for the return. So it's not so good. And when you go through Venus, is very hot. So probably the astronaut will be not very happy. So at the end, this is almost 3 years for all the mission, and this is more than 2 years for this mission. In terms of mass, we have not really a lot of ideas, but the ISS is 420 metric tons, And if we imagine Mars surface, this means the Mars base is around 1,000. So this is the mass you have to put in space to have a base on Mars. And compared to the lunar outpost, it's close to the same. Lunar 30 is quite low, it's Apollo, but lunar outpost is around 1,000 tons also. So this is why I don't believe that the American will make a real moon base, because it's very expensive and it's a key decision. The problem is that Trump announced last December that we will put America on the moon. And so this announcement was a big surprise to NASA. It was not in my plan. So if you want to, that's a key aspect of what you have to develop, to do, to put men on the Mars surface. You have to develop 11 elements. Each element could cost 10 billion, 20 million, billion, 40, we don't know. Only 2 are in development today. The SLS, which is the new Saturn V rocket that will fly 2019, 2020, and the next vehicle to put astronauts in space, this is the Orion capsule. It is an Apollo capsule. So this is fun. The other is not fun. And you will need all of this, including nuclear element, probably. Because if you want to have a base during 500 days on Mars, solar panel is not a good idea, because you have a storm, and storm can put dust on the solar panel. If you have no electricity, everybody dies. So it's not very secure. So probably you will need surface nuclear power, and this is tricky and with political issue. And what is called transitional mission and dead ends is what you have to develop during the pathway, and some are useful for this mission, some are not useful. And so there is some key decision to do. And again, the 11 are here for the Mars surface, and for example, for an Apollo type mission, you have only to develop this. So I think you understand the point. And this is for the other option. I don't want to detail, but everything is here. And what's happened? The report was June 14, and September 15, NASA issued a roadmap. And the roadmap called Journey to Mars, which is very tricky, because this roadmap is to send astronauts around the moon. So it's Journey to Mars, but what they do the Deep Space Gateway. And the Deep Space Gateway is a small station, orbital station, orbiting the moon. And you have the Orion capsule somewhere here. And what probably Europe will do is this module. So we have our niche. The Europe niche is this module. So we will part of this endeavor with NASA, doing the European service module of the capsule. And this probably will happen. This is in development, and there is a time frame for this, and this is a time frame. And at the end, this will start in 2023, if I'm correct, up to 2026-27. So in 27, this lunar Deep Space Gateway will be built, will be operational. And we will have developed some modules to be used for future Mars mission, such as the big modules to push all the modules to the moon orbit, which could be used to go to Mars. And so one remark is to decide to put an orbital station around the moon. I would say the difficulty are beyond. This means, in terms of difficulties, this is not very difficult. This means the huge effort will have to be done later. And I'm sure the industrial lobby in the US are in favor of this, because all is on the table. The module, they know how to build module. They have to build some big propulsion, so it's not very tricky. There is not R&D development difficult. And there is this aspect. This aspect is the private company, because what will be the use of the space gateway? Except the fact that the purpose is not to know what will be the use, but the purpose is to have developed the element. But there is an interest on long term is to use the deep space gateway as a fuel service station. This means you arrive with empty tank and you fill with ergol to then, from this point, you go to Mars. Because starting from the orbit of the moon is not a bad idea to go to Mars. In terms of delta V, is absolutely possible. You are far from the Earth's gravity and already quite far from the moon gravity. So it's not a bad idea to say we can start to start the voyage to Mars from this place. And some private company, I take this slide because it's one example, wants to grab a big boulders on an asteroid, on a hydrated asteroid, an EO. This means they have to go somewhere. The idea is to pick all the asteroids. It was not a very good idea because this is small. This is, let's say, 10 meters diameter boulders. If you want to find a 10 meters asteroid, it could turn very rapidly. So if you grab it, you will turn yourself. So it could be dangerous. So it's more secure to grab a big boulder on a big asteroid. And they have grabbed this. They put in the big socket, which is without leak. This is reflector toward the sun with 45 degrees mirror, and all the energy, the thermal energy, will eat the boulders, and you will crush it. And at the end, you will destroy all your boulders, and because you heat, all the water will go to vapor, and then you pump the wet vapor, and you have here you have isolation, and you will condense the vapor in this tank. So you do that close to the asteroid or close to the deep space gateway, and at the end you have a tank of water. And tank of water is useful because, as you know, water is is very heavy when you imagine to send people to Mars. But with water you can do more. You can do ergol, and you can try to have CO2, and with a lot of energy you can have CH4, H2, O2, and then O2 plus H2 is the main ergol of Ariane 5 today on the first stage. It's the most powerful chemical propulsion system, O2 plus H2. So the idea is on the table. This is interesting. All has to be done. It's not funded. This is private company. And NASA could give money to such private company. Just remember that if NASA has not spent a contract of $500 million to SpaceX, SpaceX will be dead. So with this contract of 500 million, then SpaceX have money to develop and has made the Falcon 1 and then the Falcon 9. And at the end, the investment was very good because the Falcon 9 is very cheap. And then NASA give contract, more than $5 billion contract has been received by SpaceX. So it's not Elon Musk and his pocket that pay SpaceX. It's contract from NASA, from federal budget money. And if you do the same thing with a lot of bets to such a startup company, you may win, and you may at the end have a company that have the money to develop all the system and NASA could buy the service to deliver, for example, 1 ton of propergol each month, and if you deliver 1 ton, I pay you a lot of money. And this is for the deep space gateway. The deep space gateway will be built roughly in 2027, and then what will happen? So, and then NASA plans to start launch mission to Mars. With also, again, this is the SLS. If you see a small tip here, this means there is people inside. If it is rounded, this is a threat. This is only cargo. So it's a way you can discriminate if you send people or if you send only cargo or satellite. This is something to escape the capsule in terms of failure. And so there will be mission to Mars, probably flyby, what is called, it's strange, it's not really flyby, but it's something, Mars transit, yes. Mars transit means probably flyby. And so you will spend people, and we are in around 2030. So in 2030, you may imagine that there will be some Americans that will fly by Mars. And when you read on the newspapers that the American will go to Mars in 2030, it's ambiguous. We don't know which mission is it. Is it only a flyby, it is in orbit, or it is on the surface? On the surface, my understanding is that it's not. It's impossible in 2030. It will be in 2050. It's very difficult. What are the main difficulty? So this is a list. I will go through someone here, not those one because I have no time to detail. For example, the EDL, the entry, descent, landing of a big lander with 6 people inside. What is the state of the art? The state of the art is Curiosity Sky Crane system. This is this system, which land 1 ton. But it's not enough. And the problem, it's in French, sorry. The deceleration will die the people. So Curiosity technology is not suitable, it's not scalable. We cannot scale this technology for 20 tons. It's impossible, not scalable. And it's very complex. You have 26 pyro systems that will, and the software is 500,000 lines just for this. So it's very, very complex. It works. It's a state of the art. It's the best that we can do today. It is done by the American. But we have to do more. We have to have a 40 to 80 ton system, and probably it will be necessary to decelerate before touching the atmosphere, because the atmosphere is so tiny that so weak that if you use the atmosphere to decelerate, is too violent. The deceleration is violent. Roughly, when you arrive to 9G, 10G, it's a limit acceptable for human. 15G is the die. So you have to decelerate before you touch the atmosphere, and you have what we call L over D system. L over D, say length, diameter. So the capsule L over D is 1 here because it's a circle. But L over D means you need a vehicle which is a long vehicle that will, like a shuttle. The shuttle is L over D very superior to 1. And they make R&D. This is an R&D test. This is a design, and this is not a picture, but they have done this recently, 4 years ago, 3 years ago. And it's just to test inflatable heat shield, which is very new. But today, technology is not identified. So we are at the level of R&D to do that. And the experts say that if we start now, it will not be ready before 2040. So just this element is very difficult to develop. One word for the radiation. And sorry, ladies, it will not be a good news for you. The problem is there is 2 types of radiation. There is solar particle event and galactic cosmic rays. And the energy is a factor of 1,000 between MeV, mega electron volt solar particle event, and giga electron volt galactic cosmic rays. As this is random, so this galactic is always. You have a random radiation, and you cannot protect you. It's impossible. The size of aluminium you need to protect is around 1 meter of aluminium, so it's impossible. People have think about spacecraft-generated electromagnetic field. It's a little if you want to sleep below a high voltage line on Earth. Nobody sleeps just below a high voltage line. It's forbidden. There is some chaos sometimes, but you do not that. So it's not. It's on the paper. It's interesting. So you protect by electromagnetic field, but in practice, a powerful electromagnetic field is a very unhealthy issue. So it's not. Anyway, And as I said, ladies, it's not a good news. You are more sensitive to radiation. So the criteria used by the expert is to limit the level of radiation to a level that gives you the probability to have an increase cancer in the 20 years following the flight of only 3%. This is the official limit on the nuclear industry. And unfortunately, the men, this limit is 3 sievert, and women is roughly half this limit. This means women are more sensitive to radiation. This means women will not go to Mars. That's very simple. And for the same reason, an old man is less sensitive to radiation than a young man. So maybe I can go to Mars, but not you. You are too young. And at the end, the quantity that is important is the total dose you receive during your life. This means this 50 years old veteran will have to be novice. Because if this guy has been to space a lot of time, he received a lot of radiation. So this will not happen. He may go to space during a very short period of time. But because it is a total level which is important. And as you say, this is roughly 900 days mission, and 600 days non-smoking. So if you are smoker, it's not good for you. And you have to be whole, and younger and female are limited to 200 days. So there will be some, there is a real issue. This not means that the astronaut will die during the mission. This means that he will die 20 years after the mission. So it's an ethical problem. And I'm sure NASA will treat that with an ethical working group that will formulate recommendation. The problem is to accept an astronaut that we don't accept on the nuclear industry. You know the syndrome of Fukushima. The syndrome of Fukushima was, there is a limit of radiation level where the Japanese government have to evacuate the people. This limit was written. And Fukushima arrived. The first law was to increase the limit by a factor 10. Why? Because they don't want to evacuate 1 million people. So they changed the rule. That's a reality. That's what happened. And probably that will happen to Mars. So they will accept that the astronaut will receive, so 3% is not a big deal. So this means they will be probably around 10%. And they will be at 50 years old. This means the probability to die for many, many other reasons is quite high. So it's a concern, it's not a showstopper. Just to conclude. So we have to develop probably some fission power nuclear system to have, as I said before, the solar energy is not suitable on Mars due to the storm, and so there is a political risk to send a nuclear reactor. So there is a possibility, and this possibility is to send a virgin nuclear reactor. This means this nuclear reactor has not diverged. And if the nuclear reactor has not diverged, it is not so radioactive. And after you put on a safety orbit of 2,000 kilometers, this means the time from this orbit to go down to Earth is 1,000 years, and then you diverge the reactor, you test it in flight, which is a concern for an engineer, because an engineer wants to test on ground. And this reactor we only test on flights. This means they have to design a nuclear reactor very robust to be sure that it will work up there. There is the issue, you need a big vehicle that will wait 500 days around Mars orbit. And when the crew will go, okay, we come back to Earth, so there will be a MAV, a Mars Ascent Vehicle, that will dock to this very big vehicle to go back to the Earth. The problem is all the propulsion system we use on those vehicles are cryogenic, and you cannot store during 500 days a cryogenic ergols. It's impossible. It evaporates. There is nothing inside at the end. So they have to develop a new powerful engine with stockable ergol during many hundred of days. So that's not simple to develop. Again, nuclear propulsion, we can use nuclear electric propulsion, which is the most efficient, but with very low thrust. But the ISP, which is, say, the equivalent for a car is a liter per kilometer. So ISP is the efficiency of a motor. And a big 3,000, 6,000 is very high compared to chemical propulsion, which is 200, 300. So it's very efficient, but it's low thrust. So it's very good for the cargo, but not for the crew. And for the crew, you can use nuclear thermal propulsion, which is less efficient, 1,000 second ISP, but high thrust. So again, it's have to be developed. And some consideration about the budget, and this is a slide of the report. And if you want to use this pathway, the idea is not to go beyond this dashed line. And this dashed line is written is 2.5 increase of budget per year. So 2.5% beyond inflation per year. That's the limit they give to simulate the spending of the mission up to 2050. This is why you have to go in serial and not in parallel, etc., etc. So there is different hypotheses here, but it's roughly the same thing. And with all different hypotheses, you have roughly on this curve, which is compatible. What they call budget affordability, and I put a figure of 400 billions. Apollo is 125 billion of dollar of this year, and so here we are around 400, probably 1,000. We don't know. Nobody knows exactly how much it will cost. And again, it's a low priority for most Americans. So this is why. And I finished to say that what we call the impossible that is in preparation will be the key space project for this 21st century, or maybe 22nd. Thank you.